Welcome back. Hello, everyone. I'm Nicole Avens from Tennessee Tech, and I welcome you to the afternoon tutorial session, High Performance and Smart Networking Technologies for HPC and AI. I'd like to introduce our two presenters. Welcome back, Dr. DK Panda. He's a professor and University Distinguished Scholar of Computer Science and Engineering at The Ohio State University. He serves as the director of the newly established NSF AI Institute, ISICLE. The Mbafich libraries designed and developed by his research group are currently being used worldwide. Professor Panda is a fellow of ACM and IEEE and a recipient of the 2022 IEEE Charles Babbage Award and the 2024 IEEE TCPP Outstanding Service and Contributions Award. I'd also like to welcome forward Ben Michalowicz. He's a PhD student at The Ohio State University under Professor DK Panda and Professor Hari Subramani in the Network-Based Computing Laboratory. His research interests include high-performance computing, parallel architectures, network-based computing for HPC, and parallel programming environments. Specifically, he's interested in efficiently offloading workloads to smart network cards like NVIDIA Bluefield DPUs, and Ben actively contributes to the Mbafich software. Whenever you're both ready, please go ahead.
Yeah, thank you, Nicole.
Thank you so much, Nicole.
So let me share the slides and then we'll get moving. Can you see my slides in the presentation mode?
You can now, Dr. Panda.
Okay. Okay, good afternoon, everybody. So Ben and I will be covering this tutorial. In the morning, we had a tutorial I presented together with Nauras on the high performance deep learning training and inference. There were a lot of questions on interconnects, and I requested those attendees to join here. Hopefully you are here. So this one will go into more details into the how actually large-scale clusters are being designed, especially focusing on the networking side. And the latest slides can be found here. And we also posted a link to the Slack. So please feel free to also download there. So the outline will be as follows. We'll start with a very high-level introduction, and especially asking questions like why high-performance networking, both for HPC and AI. For this tutorial, HPC and AI will be our driving applications or environments, and we'll be talking about the low-level, the interconnects, the protocols, the middleware, linking to the or helping to drive the HPC and AI applications. And once we understand like why high performance networking, we'll also try to take a look at the communication model and semantics, like think of like the application layer and the application layer and how it interacts with the lower layer. So we'll try to see, especially for communication. And then what we'll try to do, as you know, I mean, these days there are many challenges in scale up as well as scale out. Both kind of networks, technologies are coming up. We'll gradually introduce these. First, we'll start with a little bit of scale out. And in that context, we'll be taking a look at some of the very basic principles which are available in many networks, especially including InfiniBand, high-speed Ethernet, and their convergence like the Rocky V2. So through those examples, we'll actually try to understand how the basic CPU to CPU communication takes place, okay? Like a CPU on one node to the CPU on the other one. Then gradually we'll try to bring out the GPU-aware support, because these days, with especially of the AI workload and also the HPC workload, GPUs are becoming very prominent in the cluster configuration. So in that context, we'll try to take an overview of the scale-up networks, starting with NVLink, NVSwitch, AMD InfiniBand Fabric, UA-Link, Ultra Ethernet. And then once we have this kind of a reasonable understanding of some examples of scale up and small examples of scale out, then we'll try to compare and contrast with other networks. We'll not repeat each and everything. For example, we'll try to see, okay, in the cloud environment, how the Amazon has its own adapter, like an Elastic Fabric adapter. What are the features, how they are different? And then we'll also be taking a look at the Cray slingshot. This is being very extensively being used in a lot of top 500 systems. We'll see what are the kind of the features. So once we take a look at these some basic concepts, both in scale up and scale out, then we'll try to take a look at some of the smart network interfaces. And these are the new directions which are coming up. And especially here, we'll take a look at the in-network computing with the SARP. We'll take a look at the offload, like NVIDIA Bluefield DPU, AMD Pensando, Intel's IPU kind of things. And at the same time, we'll also take a look at the next very in-depth architectural issues where people are deploying high performance networking for purely for AI workload. Okay, so we'll take two examples. One is like a Cerebras, how they are designing the systems, and then how Havana Gaudi, like the Intel architecture, how they are trying to take care of the AI workload. And then we'll try to gradually come up a little bit, spend some time on the software stacks because there are some standards taking place like the UCX, Live Fabrics. Earlier we had Open Fabrics. So we'll take a look at this. And then towards the end, we'll try to give you a feel for some sample case studies and performance numbers on the very latest generation network, what kind of performance you will expect with all these different technologies. And all these numbers are taken in my lab. So we'll be able to provide like a perspective of how we have taken the numbers, how they look like. So these are not like a vendor specific numbers. These are independent numbers using our software stack. And then towards the end, we have actually a small hands-on session. This is a half-day tutorial. So we have especially looking at the InfiniBand. So we have a InfiniBand cluster. We'll go over it. We can create accounts for you if you have never run anything on a high performance network. We'll try to go through some hands-on exercises. Some of these at the low level, at the InfiniBand level, and then another one is at an MPI level. Okay, so and that's how we'll conclude. So if you take a very broad look, what is happening? These days for the last, let's say, 20 years, high performance computing or HPC has been growing in a significant manner. Okay, it is not just individual core performance, but also the chip density. Every few years, you will be seeing like almost 18 months, we are seeing also chip density is doubling. So these days, if you see like a single node, we can even go for like a 192 cores, 256 cores. And at the same time, not only CPU cores are there, the GPUs also. Commodity systems, you can get like Lambda systems, like you can get 8 GPUs, 16 GPUs. NVIDIA is going for even NVL 72 GPUs in a rack. So like this, a lot of tight integrations are happening. Okay, so broadly, you can think of like that is kind of a scale up. But then when people are talking about, I want to run distributed training in 1 million cores, so this is where you need to also use scale out networks. Okay, and that is where, especially here, we'll be focusing a lot on the commodity networks, and all these networks are trying to provide more features, more speed, reducing cost. So in that context, a generic terminology which gets used is called clusters. Okay, and the clusters is like a popular choice for scalability, modularity, and also for upgradability. And that is happening like all these traditional scientific application, let's say crash simulation, or you do nuclear simulation, or do you do bioinformatics. Now there is an interesting trend here. I'm assuming since most of you have been attending Hot Interconnect, you are familiar with this top 500 list. So this top500.org actually lists the top 500 supercomputers in the world, and it gets ranked twice a year, once in June in Europe and once in November in US. And we have taken this data. There are a lot of data in the top 500 page showing historical trends. So one especially trend, what we are trying to focus here is the trends for commodity computing clusters. Okay. So if you take a look at this x-axis, it's showing over the years what is the trend. And then here on the y-axis, we are showing number of clusters. And here it's a percentage of clusters. They're correlated. So in the very old days, if some old timers are here, you will be remembering like systems where they are called like a Cray. Cray systems, mass power systems, Intel IPSC, even IBM Bluesin. A lot of those systems you can think of proprietary. Okay, so that means they were being assembled by the companies and being sold to the users or customers. But that trend continuously changed in the early like 1990s when commodity clusters came. That means we can take a bunch of servers. That time it was CPU. Nowadays, of course, it is also CPU and GPU. And you can buy some commodity network interconnects, like InfiniBand or let's say Slingshot or Rocky 2, V2, and also scale up like a NVLink is still like a proprietary within the node. And then you can build the things not only through hardware, you can download software like a open source MPI or open source like PyTorch, and then put them together, and you have a supercomputing cluster with you. And this trend now, if you see, very almost 100% these days are all commodity cluster. Okay, except one or two. If you see like some of the Cray Slingshot is still proprietary. For example, you cannot buy Slingshot and build it in your lab. Okay, so there are few of these options are still proprietary, but most of the other networking technologies are totally commodity clusters. Okay, so not only it is just the compute clusters we care about, but since we are operating on very large data sets and all these AI workloads are coming, there is also the storage needs are also becoming very significant. Okay, so in that context, a single node, single disk may not be sufficient to hold your data. So you need like a parallel file system. Okay, so this is where also the storage clusters are coming. And broadly, if you see, the idea is very similar. You need a bunch of servers and they are connected with some network. The functionalities might be different, but physically they're very similar with some features difference. Okay, and the other one, which is really the very large market, is the data center. Okay, and almost like last 15 years, we have all been exposed to online e-commerce, e-banking. You go to purchase things over the net, and this is how a typical multi-tier data center looks like. If you, I'm sure all of you would have purchased sometimes an airline ticket or let's say Amazon. You are trying to purchase a book in Amazon. You say www.amazon.com. So you get actually connected to one of these front-end routers or servers, which is nearer to your city. And then you trying to search for a book and you put this book name and do a search, then your request actually moves to the second tier. And this is typically called like an app server. And there it actually gives you answers, like it does the search and then gives you answer saying, okay, there are so many used copies or so many old copies are available, new copies, these are the prices. It also gives you a lot of information, like those who people purchase this book they also purchase this book. They can also provide you offers. If you buy these two books together, you'll get discounts. All those kind of things get executed here. And finally, if you decide to purchase the book, then your request actually goes to the database server, and then it asks for your address, your credit card. It actually does the transaction. Then it sends a confirmation email to you saying, yeah, your book has been purchased, gives a confirmation number and gives a tentative time saying this is the time it will get delivered. So now here also, if you see, it is also a collection of physical servers and a set of switches and links. So irrespective of what we are talking, the broad commodity topology or commodity kind of configuration remains the same. Okay, and of course, many organizations they have also a combination of these. Like if you think of it like a bank, they might have the front end facing the data center where you are doing the transaction, checking your bank account and all. Might be behind the scene. They're doing a lot of forecasting, financial modeling on their compute cluster. So like this, a lot of organizations have these kind of systems emerging over the local area network, wide area network. It's sometimes even across countries and all. So then, of course, most of you are familiar with the cloud computing environments. It's a very similar idea. I mean, instead of trying to do it on premise, you are trying to do on a remote system on a cloud environment. But instead of a physical machine, they have the virtual machines. So basically, you rent some number of VMs, and then you are operating on those VMs. But the idea is also broadly remains the same. They are also only a set of those physical servers connected with some high performance networks. And now, of course, the new generation, we are talking about the AI workload. So not only you want like a very high performance training, inferencing, and these are also being integrated into the data centers, into your like Amazon. If you go, Amazon in the backend is also running some of these AI workload and trying to do you like a direct advertising kind of things. And in that context, I'm sure all of you are familiar with the LLM models, and we are like going into this. This started with very small size models, but now we have like a billions of parameters model, and people are also going into the trillion parameter models. Okay, so this computing need is steadily growing. So if you keep a very broad look at these kind of applications, just some representative ones, and if you are a networking architect, you may ask a question, say, okay, what are the kind of networking and I/O requirements? Like tomorrow, if I want to design a cluster and deploy it, what kind of features I should be looking for in the network? So then you will come up with some answers like this. So let's go into some of these answers, and that's what will drive us to go into deeper and trying to understand. If we understand our requirements, then we'll see, okay, what the vendors are trying to provide, and then we'll try to compare and contrast the features. So always, like since we are in a world of called high performance computing, nobody wants low performance, right? So especially performance has these three parameters: latency, bandwidth. These have been the traditional two parameters. The latency, as you know, to send data from one unit to the other unit. Okay, it could be one core to other core within the network, one CPU, one socket to other socket, or it could be from one core on one node to the another core on the another node. Okay, so you typically do some ping pong experiments and then try to find out half of that is the half of round trip is like a one-way latency. And especially this is important for small messages. Now, the second metric also, which have been there for many years, is the bandwidth. So this is actually for the very large messages. If I want to send it from one place to the other place, what is the rate at which I can the push the data? But the third metric, which become really important, and it's becoming very important, the debate is still continuing, is called CPU utilization. And this CPU utilization is not for application, but for protocol processing. Okay, because when you are trying to send data across the node, the question is what percentage of the CPU cycles? Okay, same thing you can also ask for the GPU also, similar things hold good. What percentage of the CPU cycles are being used for communication? And let's assume that you have two networks A and B, and they have identical latency and bandwidth. Okay, but might be one has a 40% CPU utilization for protocol processing, and the other one is 5%, the B. Which one do you choose? So you need to see, obviously, most of the answers will be B because it's the low CPU utilization. If it is 5%, that means I have 95% of my CPU cycles are left for actual computation. Okay. And if it is a 40% of the time we are spending in the network protocol processing, then only 60% is left. Okay? But then it is only purely from performance, but then in the end, we'll also bring the cost factor. Okay. So if that network B is only like a 2 times or 1.5 times costlier than network A, it is good. But if it is 20 times costlier than the network A, then you may need to rethink. So that is the kind of the dimensions in which we'll be evaluating all these different networks. So then, of course, you need good storage area network with high performance I/O, good wide area network connectivity, because as we saw, like some of these, the clusters are connected over wide area network. There is also a lot of times the quality of service is becoming very important. I'm sure when you travel in the airport, many of you might be some like a diamond medallion member, platinum medallion members, you have priority for different stages. Similar things are happening in the data center. If you are a very frequent customer of Amazon or Amazon Prime, your request will get moved faster within the data center they're trying to do. So of course, you can do some software level designs, but if the hardware provides many of these features, then it becomes much more easier to design these systems. And then another important thing is the RAS, reliability, availability, and serviceability. Because we are talking about these commodity components, they typically fail. And 20 years back, especially in the cluster world, people used to say, yeah, if something has gone bad, let's fix it in the night. These days, there is no concept of night. As you know, the data centers are running 24/7, 365. Even sometimes you would have seen, like if you lose like a 5 minutes, the systems goes down, the companies lose millions of dollars. So the question is, okay, how do you design these systems with this kind of RAS capability in mind? But then broadly, even though you want all the features, you want it with the lowest cost. Okay. So these days, the networks are becoming like the commodity, just like refrigerator, just like a car. You go, you search based on your requirement and your affordability. You try to see which car to buy, or which refrigerator to buy, or which dishwasher to buy. Same thing is happening with respect to network. So this is the big picture. We'll keep it in mind. Any questions so far? Please post your questions to Slack. And Ben, I cannot see the Slack while I'm presenting here. If you see some questions, let me know.
Very happy, Dr. Panda.
Mhm. Okay. So now with that kind of a background, now to understand this a little bit more, let's go to a very simple architecture 101. I'm sure you have taken these kind of classes in your college at some levels. And if you see like a typical server these days, we'll start with CPUs and gradually bring the GPUs. So you have some set of processors cores, there's some memory, there is an IO interface, there is a network adapter, then you connect it to the network switch. This is how a typical server looks like. And these are the hardware components. And then there is a software component, which is the communication stack. So then what happens when you are running or designing this kind of system, because since we are building commodity systems, when I say you are building, you may not be building, but like say Dell is building for you, or Penguin Computing is building for you. Okay. So they try to bring processors from somebody, memory from somebody, network from somebody, and putting it together. Okay. And depending on which components are being put together, there could be different kinds of bottlenecks. Okay. So we'll try to understand those bottlenecks first. And then in the next section, we'll see how the modern networking technologies are helping to alleviate those bottlenecks. Okay. And that race still continues. So this is the protocol processing bottleneck we'll see. Then the second one, we'll see the IO interface bottleneck. Okay. So that means you might have good processor, good memory, but let's say this IO interface where the data goes in and out is not strong enough, then you will not be able to do very high performance communication. And then the third one is the actual network bottleneck. That means I have very good servers, but then the network adapter and the network switch, depending on the topology, depending on how the configuration runs, has been set up, there could be some bottleneck there. So primarily, let's try to understand these three bottlenecks. So first is the processing bottleneck. Okay, so if you go back in the history, computer networking, we have broadly two kinds of protocol: TCP/IP, UDP/IP. Okay, so if I want to send some data from one node to the other node, there has to be a protocol which actually takes it from the memory of this node and then sends it to the other one, but it has to do some kind of processing. So in the traditional TCP/IP, if those of you are familiar, you would have taken some computer networking classes. They are typically handled by the driver, and most of the time the Linux or Windows, you name anything, it goes through the operating system, and you have to take care of like a data buffering, copies on the sender, copies on the receiver, data integrity, routing, and the standard like a ISO layers. We'll introduce that in a little bit more details in another 10 slides. There has to be a lot of signaling in between the different layers. Like if you receive a packet, it has to be a hardware interrupt on a packet arrival, and then it will do the transmission. There will be software signaling between different layers to handle the protocol processing. So if you add all these things up, even if I want to send like a 1 byte from this node to the other node, you will see it leads to like let's say 5 microsecond. Okay. So can we actually reduce? How do we reduce to live in the 1 microsecond or like a 600 nanoseconds? So we'll try to see those as a part of the solutions later on. The second one is the IO interface bottleneck. So this is the like if you look at any of your server, even your laptop, you will see, I mean, there is typically a network card, and that network card is the interface. It could be Ethernet, it could be wireless, or on the main server board, it could be like the connected to some PCI Express. So if you go back in the history, if we do to want to understand, let us go back. I mean, this is almost like a 35 years we are going back in the history. In 1990, this kind of interface was standardized, something called a PCI, okay, peripheral communication interface. So this was kind of a bus. So what it had, like there were 32-bit lines, and each one was operating on 33 megahertz. So if you do a quick math, you will see like it is a 1 gigabits per second. So no matter how powerful processor I put, memory I put, this is limited like a 1 gigabits per second. Okay. So from the memory to the network adapter, from the adapter to the network memory. And then very quickly, as the computer technology evolved in the late 90s, if you remember the time of killer micros, they used to call, the processors became continuously becoming faster in every 3 months, 4 months. So then they saw that there is a limit, so they went into PCI extended. Okay, so there are two standards were introduced in version 1 in 1998, version 2 in 2003. So here what they did is, if you see 32 bits, they changed to 64-bit, and 33 megahertz, they changed to 133 megahertz. Then the version 2, they changed this 133 to 266 or 533. So broadly, you have 2 degrees of freedom. I can either increase the bus width or increase the clock speed or both. Now, this was good up to certain time, but then gradually, if you are an electrical engineer, now you might be thinking, is this scalable? The answer is obviously no, because if you have a lot of like bits next to each other and you are changing them at a very fast speed, you will see there will be a lot of crosstalks between the bits. There will be skews. So even though you can physically design this, but the rate at which you can transfer the data will be very much limited, because the signal integrity will keep on going down. Okay, and that's what people saw towards the end of the 90s, and we'll again see how the modern technology are trying to alleviate that. The final thing is the traditional, like the network. Like, even though I build this server well, now I have a network adapter and I go into the outside of the box, and how do I connect? So here again, if you see, go back in the history, like here we are going almost like 50 years. Ethernet started in 1979, the traditional Ethernet in the computer network. So it was 10 megabits per second. And the world was very happy, if you see, for 14 years. Okay, with that technology, because at that time there was no concepts of like a Facebook or TikTok or any of the modern gadgets we are using. So the computers were only being used for like especially for some military applications, occasional emails. That was the kind of environment. Okay, so but gradually, as people started developing better software, and systems became started being integrated, then gigabit Ethernet came. There was a technology was brought from the traditional telecommunication world called ATM, asynchronous transfer mode. So gradually the speed kept on going up, and then the first, actually 1993, almost 32 years back, some of you might be remembering this technology. That was the first real cluster networking technology came. Okay, so this was from Caltech. Um, uh, uh, the technology was being used called wormhole routing. Some of you might have heard of that. And actually, that time you can actually purchase a small 4-port switch with 4 cables. That time the servers used to be very common. Servers used to be Sun Solaris server. You can connect them together and you have a 4-node cluster for you. Okay, so that's how the cluster computing started, and then that was for mostly communication. And in the following year, actually fiber channel got standardized and tried to bring even the storage in a similar manner. So then this is where, like, towards the end of 90s, we are going over the history. So then towards the end of 90s, people saw that these things are not scaling. We have bottlenecks in protocol processing, we have bottlenecks in the IO interface, we have bottleneck in the network. So this is where the community started thinking about high performance networks. So that was the broad motivation. And so there are like a multiple industry. They started working together to bring out this kind of industry networking standard. And then 2 initiatives started. One is InfiniBand and another is high speed Ethernet. Okay, and they were all brought into the market of the 2000. In the next few slides, we'll see both of these technologies. Now, InfiniBand was totally new. Okay, it was a very entire newer technologies. So that's why they aimed at all these 3 bottlenecks: protocol, IO bus, and network speed. Ethernet was already there. They also wanted to address all these 3 bottlenecks, but because it's every time, in these technologies, you have to be backward compatible. So they also wanted to be backward compatible. So they wanted to rely on complementary technologies to alleviate the protocol processing and IO bus bottlenecks. Any questions so far? Please feel free to post questions on the Slack and we can answer as we go. No questions? Okay. So then let's move this. The next section will try to build on that background, saying what is this like a high performance networking? What are these industry standard? Okay. So the InfiniBand was formed like an InfiniBand Trade Association. It was formed with 7 industry leaders. Again, some of them don't exist now, but they have been acquired by others. Now, if you take a look at the goal was to design a scalable and high performance communication and IO architecture by taking an integrated view of computing, networking, and storage technologies. So it was not just a new networking technology. They wanted to have a overall view so that if you use, you should be able to design better and better system, high performance and scalable over the years. And the first version one, was actually released almost 25 years back. Okay. And then once people started using that, people started deploying the systems, they saw some limitations in the standard. And then several annexes were released over the years. Like some of these names you might have heard from some literature and all, RDMA-CM, iSure, XRC, Rocky V2, virtualization, all these things gradually got added to the standard. And the very latest version is 1.8, and that is there in the September 2024. If you go to this site, you should be able to completely download the standard. Okay, but make no mistake, if you download, this is 1700 pages long, 1700. Okay, so please don't try to read all these things. And even though like in this tutorial, we'll not be able to give you all the knowledge. Okay. But at the same time, as a general practitioner, you may not need all this knowledge. Okay. So in this tutorial, what we'll try to do is we'll give you the basic ideas, basic knowledge, so that you can appreciate what is there, what is not there. But if you are an actual designer, if you are working in a company saying, okay, I want to design this InfiniBand adapter, of course, you have to look at the standard because you have to match with the specification of the standard. Then similarly, as this InfiniBand consortium was coming up, was being released, the standard, similar effort was going on the Ethernet side. So this was being named at that time called high-speed Ethernet. And if you remember, like we had 1 gigi was already available. So then the next jump was 10 gigi. It was formed by several industry leaders, and the goal was exactly same as InfiniBand, to achieve a scalable and high-performance communication architecture while maintaining backward compatibility with Ethernet. Now, what happened, 1 to 10 was good, but then over the years, as InfiniBand keep on moving, we'll see it in the next few slides, some of these components like the interface, the cable, the SerDes, the question was like, can they be used for both technologies? Okay, so this is where I think there is a lot of things goes back and forth between these two technologies, and especially Ethernet, if you remember, after 10, it always a multiples of 10. Like we started with 10 megabits, 100 megabits, 1 gig, 10 gig. The natural progression was 100 gig. But at some time, in the time, even though like you can build a 100 gig adapter, but the IO interface was not there. But IO interface was available for 40 gig InfiniBand. Okay, so that's why you will see there was a lot of discussion happened. There were like here IEEE 802.3 working group was introduced to introduce 40 gig server. Then later on in 2014, they even went down for a 25 Ethernet consortium to leverage the technology, what is happening from the InfiniBand side, so that the same hardware kind of things can be used, same hardware components can be used. So like this, both these technologies going back and forth over the years. And in fact, we'll take a look at even these days, there is a lot of this debate or the war between InfiniBand and high-speed Ethernet has been there for the last 25 years, and it's still continuing. Okay, so we'll take a look at that in the later slides. This Ultra Ethernet Consortium has come, the scale-up Ethernet has come. So like this, a lot of these efforts are happening. So now let's see how both these technologies, InfiniBand and high-speed Ethernet, try to handle these bottlenecks. We'll exactly take a look at those three: network speed bottlenecks, protocol processing bottleneck, and IO interface bottlenecks. So if you take a look at InfiniBand, if those of you don't know, the InfiniBand, the name was coined from 2 words. It stands infinite bandwidth. Okay. what does actually infinite bandwidth means? I mean, there is nothing like in the world really infinite. Okay. But what they did, if you remember, like the PCI Express, PCI and PCIX, when we're talking about the bus-based number of bits and each bit can be moved, and that was the kind of the limitation. So to alleviate that, this newer standard introduced something called bit serial differential signaling. What does that mean? So it's an independent pair of wires to transmit the data, but it was like a put together. Okay, so you can think of it's like a one pair, and you can have multiple of such pairs. Okay, and each pair was shielded, and then you can have multiple of such pairs being put together into a cable. So the same 2 degrees of freedom remained, like it is scalable to any number of lanes. So this was like a one pair was called a lane. So I can have 2 lanes, 4 lanes, 8 lanes, 16 lanes, etc. And then the speed of that lane. Okay, and since each one is like a twisted pair and they are shielded, so that crosstalk issues don't arise. Okay, so that was the main thing. And then you can actually, the idea was that both these parameters, the clock speed and the number of lanes, can be changed as the demand grows. That was the key thing. And that's what exactly is happening over the years. And if you can achieve that, that's why theoretically there is no perceived limit on the bandwidth, and that's how the name came as infinite bandwidth. Okay. So let's see how that actually works. Okay. So this is a very dense slide, but let me go step by step. So we had seen all these technologies earlier. So this InfiniBand, the standard was introduced in 2000, October 2000. The product came out in like 2001. So what they had in the very beginning, here you can see this terminology. It was 1x. X is the number of lane. That means there is a one lane. And the rate, what they had is called single data rate. That means if you remember the digital logic, one clock. So it was trying to send one bit for clock. Okay. And the base rate was actually 2.5 gigabits per second. That was as a physical. And most of the time, the networking, this concept has been there many times. I mean, there is a physical layer, but there is a payload layer. You try to add some bits for parity, for error recovery, those kind of things. And that time it was 8 to 10 encoding. That means if I have 8 bits from the top, I expand that into to 10 bits and then send it. So there is an overhead. So effectively, the payload was 2 gigabits per second, but under the hood, it was 2.5 gigabits per second. Since we are normalizing across InfiniBand and Ethernet, we'll just show the payload rate. Okay. So in the same year, 2001, 10 gig came, and the payload was also 10 gigabits per second. So effectively, below it was going as a 12.5. Okay. So then in 2 years, if the demand increased, what happened, if you compare this with this, the SDR remained the same, but they increased the number of lane, 1x to 4x. Okay. So instead of like a one twisted pair, now you can see like a 4 of these being together in a cable. So now you can see the bandwidth increased from 2 to 8. So then in another 2 years, so these are all like being defined by the InfiniBand, the standard consortium, the trade association. So they look at the market, they look at the demand, and then keep on coming up with the next and next standards. So in 2005, they kept the same 4 lanes, but the SDR was changed to DDR, double data rate. So that means I have like a one clock. Instead of sending only 1 bit, I can send 1 bit on the rising, 1 bit on the falling. So now you will get effectively double the bandwidth, 8 to 16. So in fact, during that time, this was like a 2005, IBM actually had a product. They had a 12x SDR. Okay. It was delivering 24 gigabits per second. But the question, they were way ahead of their time. Like how the world was operating, they had a very nice product. But what they found out that they couldn't, I mean, it was, first of all, it was very expensive. And the second thing was, it was not a technical issues, but there was an engineering issues because these cables were so thick. There are 12 lanes. So what was happening is that if those of you know, like how the servers are designed, like I have a server, the network adapter actually either goes like this or goes like this. So this big cable was trying to bend these NICs. Okay. So they didn't know how to really engineer a cluster. So actually that technology died down. Okay. But they were way ahead of the time. Okay. And in 2007, now you see the technology again advanced. Instead of DDR, it moved to QDR, like a quad data rate. That means in the one clock cycle, we can send 4 bits. Okay. And that gave the bandwidth from 16 to 32. And then during this time, this was like a 32 gigabits per second. The physical was like a 40 gigabits per second. And then that's how the Ethernet consortium debated. And instead of jumping from 10 to 100 megabits, they actually, sorry, yeah, uh, 10 gig to 100 gig, they moved into this intermediate one, which is the 40 gig. And then in 2011, this was a little bit of odd, but it happened like that. The QDR was like a quad data rate. In the binary, you go 1, 2, 4, 8, 16, but they had some intermediate. They had a FDR, which is called 14 data rate. That means in one clock cycle, they were able to send 14 bits. And interestingly, during that time, in the 10 years, that 8 to 10 encoding, which happens below, that technology also got enhanced. So instead of trying to wasting 20% of your bandwidth, they had like a 64 to 66 technology, encoding technologies. That means if I just put only 2 additional bits for 64 bits, I can actually recover the errors. So if you do some math, that's where in the very 2011, InfiniBand was moving into like a single port. You can have 54.6 gigahertz per second. And sometimes, these networks have dual ports. And if you do a channel bonding across both the ports, you can effectively get 100 gigabits. So that's how the InfiniBand moved to 100 gigabits in 2012. And then the Ethernet was following. I mean, here it was like a 40 gigabit Ethernet. Then they wanted to reuse some of the SerDes and all, as I was telling. So they downgraded this a little bit to make it cheaper. So this is where like a 25, 50 gigabits per second was introduced. And then actual 100 gigabit Ethernet came in 2015. Then in the InfiniBand, also there were many different companies to start with. Gradually they shrunk. There was one company called QLogic. They introduced something called OmniPath. So that was they had a QLogic which was InfiniBand, and they were using, like, instead of Melanos going through offloading path, they were using an onloading path. That means they were doing the protocol processing in the CPUs, because by that time the number of cores were larger. So the idea was that, okay, instead of making the network much more costlier, can I dedicate some cores to do protocol processing? Okay. So that was a QLogic InfiniBand, and gradually Intel purchased it, renamed it. That was like a OmniPath was introduced. Okay. And then InfiniBand again moved to EDR, enhanced data rate, that was 100 gig. Then HDR, high data rate, 200 gig. Then Cray Slingshot was introduced. Cray also had the earlier history like Gemini, those kind of network. They moved to 100 gig. Then this Intel had purchased QLogic, but they also got split. This is where the kernel-less network was a new company got formed. So they had this OmniPath Express 100 gig. Google and all these different vendors, they also were pursuing some of these technologies. Google had his own network called Aquila for their in-house consumption, but it never actually made to the real production. It was a research. And then InfiniBand introduced like 400 gigabits per second, 4x NDR. And just last year, even the kernel-less network introduced the 400 gigabits per second called CN5000. Okay, so like this gives you a very quick history of what has happened over the years. So now you will see, like, starting from like a 2001 to 2024, this bandwidth has improved by almost 200 times. Okay, and that we keep on seeing over the years how these networks are able to give higher and higher bandwidth. Any questions on this slide? There's a lot of information, but it really brings the history together. Any questions on the Slack, Ben?
None that haven't been answered already. I've been taking care of each one that's been popping in.
I can't hear you.
No, sorry, no, I was saying that I've been taking care of each question that's been popping in from the attendees. Am I audible?
So let's continue. So Ben,
Oh,
I can't
hang
hear
on.
you. Are you
Can you
still
hear me?
there?
Yeah, I'm still here.
Okay. So let's move to the next one, which is the protocol processing bottlenecks. Um, so in the protocol processing bottleneck, so the idea came like as this modern network started evolving, the if you put more functionality on the network, and this was actually very early days. I mean, nowadays, whatever we call like a smart NICs, people used to call like an intelligent network interface cards. Okay. Um, so the broad idea here, I'll try to introduce these concepts of executive and assistant. Okay, or you can say executive and secretary. And we'll use that example throughout this tutorial to introduce other concepts also. So I'm sure you have, like some of you attending this today's tutorial might be managers, you might have your assistants or secretaries to extend help to you. Okay. Now think of you as a manager, you hire actually your assistant or a secretary who is a PhD degree holder. Okay. What can you offload? The answer will be everything. All right. You can ask this your assistant to write for a research grant or write for a commercial contract, get the money, do the development of the product, or write the paper. You just say in the end, even submit the report, deliver the product, and say just put my name there, right? So because they have the PhD degree, you can actually offload quite a lot there. But of course, the question is like it will be very expensive if you want to hire a PhD degree holder. On the other hand, if think of like you have hired an assistant or a secretary who has a high school degree or like a 2-year college degree. Okay, so then the question is, okay, you can only offload small parts. Okay, might be in a big proposal writing, you say, okay, collect the references, or you say, okay, send all these emails. So like this, you typically send the information. So that is the thing. What we'll see as we get introduced to different technologies, we'll see the vendors are trying to put different amount of kind of offloads. Okay, so there is a cost performance associated with it. So that is one thing we'll see. So there have been some hardware like a TCP offload engines or TOE. You will see you can support the entire protocol processing completely in the hardware. So you can have hardware protocol offload. But offload is one, but then the question is how the executive and secretary talk to each other. Okay. So this is where we'll try to introduce this kind of protocol processing bottleneck. If you like, let's say, for example, if you're a manager, you had an assistant with you for last 10 years, he or she knows exactly what you do. So depending on the month, depending on the time period, depending on new events, he or she knows what to do. Like a might be hot interconnect, call for paper came 3 months back, you know exactly how we need to submit a paper or submit a presentation there. Okay, so that means with only few words, executive can talk to the secretary or the assistant. Okay, and that's what we call like a rich communication interface it provides to the application, and that's what in the literature is known as something called a user level communication capability. And in the next section, we'll see how that gets actually implemented. And sometimes also people have given names like a voice bypass protocols, kernel bypass protocols, and those are the capabilities which actually makes all these offload very efficient. Okay? And there we'll see like this doesn't go through all those software signaling. We talked about the standard TCP/IP, and that's how these days, if you talk to any of the modern networks technologies, you can actually do even the node-to-node communication in 1 microsecond or even lower. Okay. So the final bottleneck we'll see is the I/O interface bottleneck. Okay. So there is interesting issues here. We'll see if you remember the InfiniBand when we started, a typical communication from node to node happens memory to memory. Like a memory of one node, the data is sitting, so you need to move it and then move to the memory of the other node. Of course, the I/O interface is used, network adapter is used, network switch. That's how the data moves. Now, in InfiniBand in the beginning, it introduced this bit serial differential signaling. What it means, it actually tried to replace that I/O interface. Whatever the PCIX was there, it wanted to totally change it. But if you think that time the InfiniBand standard was coming from a purely networking standard. Okay, they didn't have any like a control over servers. the servers were still being controlled by Intel that time. AMD was just coming up that time, but the primary one is the Intel. And Intel, if you go back in the history, they had a front side bus. They had their own internal architecture. They didn't want to expose that, okay? Or rather a third party to come and then tap into their memory bus. So a lot of debate happened. So in fact, if you go back and do a search on the web around 1995 timeframe, even though Intel was a part of InfiniBand standard in the beginning, it actually officially withdrew. Okay, it wanted InfiniBand to die so that their technologies continue. And once InfiniBand withdrew, Microsoft also withdrew. Okay, so there was some chaos at some time in the 1995. But what was happening? Another thing, interesting thing was happening during that time. The GPU technology was coming up. Okay, so the GPU technologies, if you remember the basic principles, of course, now a lot of things have changed in the last 15 years, 20 years. For the GPUs, you also need to send data to GPU before it can work. And then after the GPU gets done, then you need to move data back to the CPU. And that was happening over the same PCI-X. So what was happening? The GPU users and all were also not very happy with Intel. InfiniBand and the networking community was also not happy with Intel. Okay, so it was Intel was being banged by both the sides, and if hot interconnect, I mean, even though it is a virtual, it's being driven in the Bay Area. Companies in the Bay Area always like this kind of competition always exists. First, you try to compete with your competitors, but if you cannot win, join the competitor, okay, because you want also the market share. And that's what exactly Intel did. So what Intel introduced, that was the time it introduced called PCI Express, PCI Express. Okay, so now if you see the PCI Express, this side exactly borrowed the same idea of InfiniBand. Okay, like it has number of lanes, and each lane can actually operate at certain rates depending on how many lanes you provide in that I/O interface. You can actually have both the degrees of freedom, and then you can actually keep on building more and more better bandwidth. So that's what happened. After that, recently what has happened is both InfiniBand or high-speed Ethernet today come as a network adapters that plug into existing I/O technology. Even though all the GPUs go into the PCI Express and all, it continued for some time. And again, when we come back to the GPU section, you will see that conflict still existed. Okay, it never went out, and that led to the birth of NVLink, which is the scale-up technologies. Okay, so we'll hold that discussion a little bit later, but we'll see that this kind of bottleneck issues become actually big issues, and then newer standards and all get introduced. So that's what happened here. If you see, because of the PCI, even though PCI Express, it started with Gen 3, then Gen 4, then Gen 5 is the most common one. Gen 6 has been announced, but there are not many systems out there. So over the years, if you have a better GPU, if you have a better accelerator, if you have a better network, people try to get higher bandwidth to the memory. Okay, so this is where all these consortium started, like CCIX, NVLink came. I'll go into that detail a little bit later. Then CAPI, OpenCAPI, Gen G, they kept on some time and all they died. Except NVLink. NVLink is still going very strong. But what evolved from this, something called CXL, which is Compute Express Link. Again, the idea is that, okay, so it's a cache coherent interconnect. So that means I can actually have multiple servers within a rack talking in a cache coherent shared memory manner. Okay, so that if each server has like a 16 gigabytes, I can have 8 of these connected to make it like 128 gigabyte or memory kind of thing. And this has evolved. The very latest is like it started with CXL1, continuously going to CXL 3.1. There are some products out there like companies like Nfabrica, I think XGen or XCon. I'm not. I'm forgetting the names. So there are a lot of products out there which are coming with the CXL. But then, since NVLink is there, this is where also the UL link is also coming into picture. We'll cover that in the little bit later. So these are all competing with each other. The CXL, UL link, Now, very recently is the scale-up Ethernet. So all of them are in the same space, competing with each other, and then we'll see which technology actually moves forward in a much more stronger manner. Any questions so far? Ben, let me know if there are any questions on the Slack.
Dr. Panda, can you hear me now? Okay, guess not.
Are there any questions? Ben, I can't hear you. Are you sure you're talking, telling me something, or? Let me see. There's some chat. Okay, okay. Yeah. The attendees can hear me? All right. Ben, I can't hear you.
Check test 1. Can you hear me?
Okay. Mm, the attendees can hear me, or I'm just talking to myself? Sorry. Okay, okay, good, good. So let's continue during the break or something. We'll see what exactly is happening. Okay, so yeah, so Ben, I can see the chat. So sorry for problem. Okay, so let's move. So next, what we'd like to see, like we have these technologies, but before we jump into the individual details, let's try to see how the upper layers communicate with the network layer. Okay, and that's what we'll call like a communication model and then the semantics. Okay. Mm. Okay. So broadly in the networking world, there are like two models. One is called a two-sided communication model, and another is a one-sided communication model. Okay. So the two-sided communication model, you can think of like a uh, just think of mail, the email. Like let's say I'm sending you an email. So it is actually a two-sided protocol. That means even though I send you first, let's say I want to send you a let's say very big file. The question is whether your mail server can handle it or not. Okay. And these days we don't see that issue. Sometimes some mails like Outlook, it says, okay, if you send a mail bigger than 25 megabytes, it will not go. You get a rejection. All right. But then if a mail goes and reaches your mailbox or mail server, what happens to that mail is totally the control lies with you. I don't have any control. Am I right? You can say, oh, I received that email from Dr. Panda. I should put it in a folder or I should delete. Entire control lies with you. Okay. So that's how these networks also operate. Okay. So here you will see some animation here. So let's say there are these three HCAs. SCA we'll call like a host channel adapter or network adapter. It's a infinite terminologies, but you can name anything. There are three processes or three processor cores. They're talking to each other. So in the beginning, what happens is before I receive something, typically I want to get the very high performance. So I typically post some receive buffers. Okay. It's just like the mailbox I said, if I want to hear from somebody, my mailbox I should have some memory. Okay. And here I post some receive buffer with some information. We'll see later on. Similarly, let's say P3. Also, I want to get another message from P3. So I'll post two buffers, one for P1 and one for P3. And then since we are talking about high performance communication, there is a polling engine. Typically, you can either go through communication networking protocols like either polling or interrupt. Most of the time we do polling. You can also use interrupt. Polling automatically you get the data. So I will be continuously polling, and then on a P1 and P3. So let's say P3 performs the computation and ready to send the data to P2. It will send. Now you see the animation. So it will come to the network, and then the network will actually send. So here it sent. It was received by SCA, but since it was getting polled, quickly it will get the received data and then continue. Okay. And then similarly, if once P1 sends it, it'll actually come and then gets it from this P2's adapter will get it from P1 and then continue. So it is actually, later on we'll see, there has to be some mechanism in the adapter to know from where the message came. There has to be some kind of a matching has to take place here. Okay, because I posted a buffer from P1, buffer from P3, I should not be getting the other way around. Otherwise, the program will lead to incorrect behavior. So the data which came from P2, it'll be collected in that buffer P3, and then from the orange one, whatever I posted, it should be collected from the P1 into that buffer. So this is a very two-sided protocol. So there is some overhead, but it is asynchronous. I mean, it can go independent asynchronous, but there is some kind of a synchronization you can see. All right. So these are the kind of the broad synchronizations are taking place. But there is an advanced protocol which is called one-sided communication model. Okay. So before I go into that, let me give an example. So this is like a think of like you have you have a lot of books or files on your file cabinet or a bookcase, and if your colleague wants to borrow a book or wants to borrow a file, there are two ways. Either they can follow the two-sided, that means they come to your door, they knock it, you then they talk to you saying, okay, I would like to take this book. You take the book and give it to your friend. Okay. But if your friend is a trusted one, okay, you have a very good relationship, you can tell your friend saying, please don't worry, as long as my door is open, you can come in and take the book. Or even sometimes you say, okay, even if it's very much trusted, you say, if the door has a key, you give that key to the other guy or your colleague, saying, even though I am here or not, you just come to my office, take it, and after it is used, give it back. Okay. So that is the kind of the one-sided model is very significantly being used in the modern day technologies and the modern day upper level software. So let's see what that means. So typically any kind of a software, so just like the example I gave, like the my colleague and all, that means I have to give some kind of a permission to my friend, whether through a key or to actually a physical key or a digital key or some kind of a permission. And that's what happens. Any software, typically, let's say, for example, here you create some buffers and you exchange the addresses of these buffers. Okay, so you create some global region. And then what happens, you will see that, let's say, I want to send a data to P3. Let me go back and then I'll do it again. So now as soon as you write, you will see that earlier it was going to P3 SCA, then there was a matching was taking place and then it was being written to the memory. But now we don't have to do that. So see the things here. It came here, it directly went to SCA and it got directly written to the memory. Okay. And then same thing happens, like if a P1 writes data to P2, so it comes to the adapter completely writes. So that means the sender is able to tell the receiver where to place the data. Okay, so this is called the one-sided communication. Okay, and in few more slides, we'll have more animation to tell you how exactly it happens. But then if you can do it, you will see that that provides a big opportunity for overlap of computation with communication. So that is the key thing. Okay, so like this, if you see here, P3 might be continuously doing the computation. It doesn't have to be interrupted. So data automatically comes and gets deposited into the memory. And at later time, it can actually do some checking. There are some mechanisms to check whether the data has arrived or not. And if it checks that the data has been arrived, then it continues. Okay, so that is the big benefit of this overlap of computation and communication. So you get much more like your applications, even though your communication takes more time, you can actually overlap. So the effective overhead of the communication goes down. Okay, and that gives very good performance, scalability for your end applications. And these kind of techniques are being extensively being explored, not only in the hardware level, in the middleware level, and also the software level. But in order to achieve all these things, you need to do a little bit more. Okay, so let me go into that. So here, if you take a look at like the typical, like I have an adapter, then there's a kernel, then there's a process. So the idea, if you even in the one-sided, two-sided, you remember we are saying some buffers. Buffers have to be defined. Buffers have to be something called a registered. Okay. So what does that mean? So the broad idea, if you see anytime, I mean, these are the modern day software, everything you write in a virtual address, right? Nobody writes programs in physical address except you go to the firmware, there everything or a DM engines, they work on physical addresses. So at a top level, when you say, okay, I need to send this data from this buffer to this other buffer or this buffer to the processor, you basically send like a virtual address. But before you send the data, with all this modern networking, what you need to do is something called register. Okay. So that means the step one is saying it is like an intent to send. That means I'll be sending data from this buffer. You first tell to that kernel, and kernel actually has to go through the virtual to physical translation. I'm sure all of you would have read about like the paste tables and all, because it takes a lot of time to do the conversion, and this has to be done by the operating system. Okay, otherwise will be security issues will be cannot be guaranteed. But then what happens once you do that? Once you do the virtual to physical address translation, not only the address gets translated, but all these modern networks have something called a cache. Okay, this is very different than our physical cache, like a typical, the CPU memory hierarchy. We have L1 cache, L2 cache, L3 cache. This is not the cache. Within the adapter itself, there is a small amount of memory which is caching this virtual to physical address mapping. And then what happens is it issues two kinds of keys. One is called a local key and another is called a remote key. So these keys are now given to the back to the process. Okay. So this is just like it happens, either it can happen initialization or it can happen in the background. The main thing is not to do it in the critical part, critical communication. Okay. But when the actual communication takes place, this is how it operates. Okay. So that means the same handle, you got it back. Now let's say the process wants to it finished the computation, it wants to communicate. It actually not only tells the NIC saying, okay, send the data, it has to actually present that local key, because I'm talking to my local adapter. I present that local key. So the adapter actually has already the cache. It looks its own cache. Now I don't have to go through this entire translation. So that's why if you see, it is not going through the kernel. Okay. It is going directly, like the process is directly talking to the NIC. Okay. And this is something you remember, if you 10 minutes back, I said, if you have an established assistant or secretary to a manager, the manager just tells, okay, hot interconnect is coming. That's all. The assistant knows what to do. Okay. Think of like that, because the assistant has done this so many times. It has that information in the cache. So then it sends, and this is what is known as kernel bypass protocols, or sometimes we known as OS bypass protocols, operating system bypass protocols. And this is an example of local key. This is like the local send, like either you do two-sided or one-sided. But if you are trying to do a one-sided from a remote, so then here you will see like the remote process, not only it sends the data, it has to actually send the R key. Okay. And of course, you have to do some exchange of the R key in your initialization time. And this is where, when InfiniBand started in the very beginning, this R key was not protected or not encrypted. Okay. The idea was that all this communication will happen in a data center, and in that data center, everything is inside. So then people can actually talk there. So, but now once things went to the wide area network, and then the kernel bypass grants, so once it went to the wide area, now there are routers and all which actually do online encryption at the very fast rate. Of course, these are very expensive, but it also provides very good performance as well as encryption. And then this is the kernel bypass grants actually that improved latency. Okay. So when we are talking about like a sub-microsecond latency and all, node to node, these are the actual things, what is happening. These are the techniques which is happening below, and these are very critical to the latency reduction. So now let's try to now bring a few more concepts, and we'll all put put it together before we jump into the next section. So even in all these modern networks, these are some examples of InfiniBand, but all the other networks have very similar terminologies, similar concepts. So if I want to send some things, it calls like there is something called a queue pair. Okay, like I have to establish a queue pair before I talk. Okay, so then typically, these assistants in the old days, when they're sitting, your secretaries in the desk, there used to be something called a in queue and out queue. Okay, like the mails come, the mails go out. So similarly, within our software stack, here there is some send queue, receive queue, then send something called a completion queue. So that means the messages need to be posted. This is called a work queue element or called a wookie. So you post things into the wookie, and then once the operation gets done, you take it back, and these are called completion queue element or cookie. Okay. So like this, there are different kinds of work queues. There is this hardware, which is the actual engine. It tries to multiplex between all these work queues. It's just like a secretary. Yeah, you keep on giving tasks, or even multiple executives can give tasks. The secretary is doing all these things and informing in a completion manner, saying this X got completed, Y got completed, G got completed, etc. Okay, so that's how these modern networks work. So now all these sections, let's put it together. These are very nice animation slides, thanks to some of my older students who did all this thing, but it actually visually brings it out how these protocols work. Okay, so we'll start with the send receive model. So here you will see that so let's say this is the sender side, this is the receiver side, and I have the queue pair, which is send queue, receive queue. I have a completion queue. These the processors are there. This is the memory. Okay. So as we saw in the two-sided protocol, receiver has to post a wookie. Okay. So this is just like we saw earlier. We said buffer. We are refining that concept. So this has actually information on if I get a message, where to put it. Okay, it's just like you have a mailbox. Many people do multiple folders, like based on who sends the message or from whom the message is received, they put it into that folder. Okay, so think of like that concept. So on the sender side, also the sender posts this wookie. This wookie has information on where the data needs to be sent. Just like the receiver says, okay, if I get it, where to put it, how to put it. Sender side has exactly the other thing, saying, yeah, I need to have either the data is contiguous, either the data is non-contiguous, size of the data, and all those things. Okay. So then after that, what happens, the processor or executive is totally, they don't get involved. Okay. So the adapter, in this case, the InfiniBand device or the secretary takes that wookie, think of like a descriptor. It gets, and then there are multiple DM engines in the network. It tries to go, gets the things from the memory, and then puts into those packets. It goes through some like a physical layer, the link layer and all. It sends the data over the switches and it reaches the destination, SCA. But now, since it is a two-sided protocol, this information, it's only now there is a second step needs to be involved. So has to be a matching here. Okay, so that adapter actually now trying to do a matching, saying, oh, it was a buffer was posted here, okay, and now I need to match with that and then get the information saying where the data needs to be written. Okay, and then once the data is written, then receiver side, you put an entry into the completion queue saying that the data has been received. And then the executive can keep on polling on this or even can get an interrupt to know that something has been received. And then you send the ACK back to the sender. On the sender side, it knows that the data got delivered. It also puts an entry in the completion queue. And then the sender can actually now come and then poll and determine that it got received. So this is how both the sides actually work together to exchange the data. Now, if you see here, these processors are involved only to post receive key, post send key, and pull out the completed cookies. That's all they do. Okay, and these leads to the concept, if you remember, I introduced from the very beginning, saying CPU utilization for protocol processing. Okay, so that means here we are offloading most of the things to our assistants or secretaries, in this case, the intelligent or the intelligent NICs. And I need to send only very little CPU cycles for communication. So the most of the cycles are left for computation. whether it is HPC or AI or any of the upper level workload. So that is the send receive model. So now if I go into the one-sided model, which is also matches with this RDMA model. Okay, so this is where this RDMA concept started coming, like a remote DMA. So DMA, you know, has been there in the field for many years. Even in a single server, I can actually send data, like instead of processor continuously doing load store, it actually gives the DMA saying, okay, gives a start address, end address, and tells, okay, you do the transfer. Okay. Now RDMA actually extended the DMA concept to across the node. Okay. So now you see the same thing in an animation form in the very beginning. Now, since it is a one-sided operation, or sometimes is known as memory semantics, on the receiver side, I don't have to post anything before the communication starts. Okay. The sender side, when it posts this wookie, it has information about both the send buffer as well as the receive buffer. Okay. That's what we saw in the previous example. You remember? And then now you'll see that there is a difference. Earlier, the message was coming and reaching the destination adapter, but it was waiting there for a matching to take place. Now we don't need to do that. So now you see the data will come and directly gets written to the memory. Okay, because the packet has information not only on the sender memory, it also has the information on the receiver memory. Okay, and then actually you get an hardware act, and then you know that it was delivered. Okay, so this actually shows the real overlap. So now if you see, even the receiver doesn't have to do anything. Okay, so it has like a very little thing, post send key, pull out the completion key, no involvement from the target processors. Okay, so that is the beauty of this one-sided or RDMA semantics. So if you design the upper level software stack properly with the appropriate support from the under the network, effectively you can do 100% overlap on the receiver side. Okay, so that means continuously data will be coming. I'll be busy with my computation. And of course, there are some techniques to do some pooling, like a pooling on the last byte or pooling on a small message to know that the data has come, and then you will continue to operate. Okay. Any questions so far? I mean, this is like a very basic principles we have put together in this section to make sure that almost all the networks follow the very similar principles. Any questions, comments here? Again, I think give me a minute. I think I don't know why I'm not able to hear you. I was hearing you. Just a minute.
Can you hear
Sorry
me
for
now?
the technical issues. I'll stop it. Okay.
So folks, just a heads up, Dr. Panda is currently fixing some audio things. Indira, I have passed on your question to Dr. Panda. He should be able to answer it. And then Sharif, I also make sure Dr. Panda sees this as well. In the meantime.
Yes, I can hear you now.
Awesome. Okay. So yeah, so Dr. Panda, so we have two questions. One from Indira K saying that mentioning the notion of DPDK and its own bypassing kernel. They're asking how is it different from InfiniBand's bypassing kernel?
Yeah. So there are multiple of these. What I mentioned is the basic principles. Okay. So of course there are different implementations of this. There is a SPDK, there is a DPDK. So there are different variations of these, and different vendors are actually putting it. If you go to very latest, even like let's say NVIDIA has UCX, now they have a DOCA. So we are not indicating any very specific things here. We are just indicating the basic principles. Okay, but they do it at all different levels and with a different kinds of overheads. But the concept remains the same.
Awesome. There's a question from Sharif Jazra, I hope I pronounced that right, asking the question, does the RDMA model push the need for queues up to the processors?
Need to push the queues.
Yeah, does the RDMA model push the need for queues up to the processors?
So hold on a little bit more. In the next section, we'll try to actually bring the concepts of virtual lane, service levels, those kind of things. We'll see there is with those kind of here what I introduce is just called a queue pair. Queue pair is an abstraction. Okay. From a processor side, you can have multiple of these queue pairs. Okay. And you can provide a quality of service saying, okay, this queue pair will be used for point-to-point communication. This queue pair will be used for collective communication. So like this, in that sense, yes, sometimes the requirement can go up to the processor. Okay.
That's all the questions we have for now.
Okay. Okay. Sorry for the interruption. I don't know why that the thing stopped working, but let me continue.
Before I continue, Dr. Panda, are we still on top? Are we still on track for the break in 20 minutes?
Yeah. So we'll have a break in another 20 minutes. That's correct. Yes.
Awesome. Awesome. Okay.
So we'll continue, and then you can see my screen, am I right?
Yeah. Yes, we can.
Okay. So what we'll do in this section, since we now understand the basic principles, so in this section we'll at least take two of these. Okay. InfiniBand and high-speed Ethernet, especially Rocky, and then try to bring at least the first part. We'll say, okay, how this convergence is taking place, and then we'll try to go through this the GPU aware support, and then gradually we keep on moving. Okay. So here, so what we'll try to see here, like InfiniBand, the basic architecture, hardware components, some of the protocol offload. We'll also introduce very briefly the iWarp, which has been a technology has been there for some time. It's not very popular nowadays, but it's still there. It's a purely kind of a RDMA and with Ethernet, and then we'll talk about the Rocky. So if you take a look at this left-hand side is the traditional Ethernet. Many of you must be familiar with saying we have a physical layer, link layer, network layer, transport layer, application layer. And typically here you see there's some management tools. The transport layer has TCP, UDP, sockets interface, and then you have this application. Now, if you want to understand either InfiniBand or any of these other Slingshot or anything, you'll see here we'll just give you an InfiniBand, but you can do a similar comparison with your favorite network. So physical layer, let's say copper or optical. Then you have a link layer, and this is where there is a network, especially in the InfiniBand context, is called subnet manager, and open subnet manager, that is like the open source version, is like a management tool, okay, which allows you to configure the network and all. We'll see some examples later on. So then you have the network layer, which takes care of routing, just like the left-hand side. The right-hand side, when the network InfiniBand started, it had a lot of protocols. Most of the common ones are called RC, which is reliable, which is very equivalent to like TCP, and the UD, which is like unreliable. Okay, but later on, actually, this need of XRC came, and in fact, the Amazon AWS EFA will see something called SRD. So like this, there is a lot of newer protocols are coming up. But the biggest difference here, in the Ethernet world, any of the software layers talk to the bottom layer using sockets. And what InfiniBand started with, and all the modern networks also have an equivalent, is something called a burst, which is very low level. You can think of low level set of instructions or commands to communicate with the the network, and then all the other software layers are built on top of this. Okay. So here, if you see, so we'll actually, the next few slides actually will go through a series of very nice again animation to illustrate the concept. So if you take a look at this, let's say very top level applications or middleware. As I said, in the traditional Ethernet world, it goes through the sockets, and the leftmost column here is pure Ethernet. That means it goes through the kernel, like the Ethernet driver, Ethernet adapter, Ethernet switch. Okay. Now, every time a new networking technology comes, so this is a chicken and egg. That means all the ecosystem is not available. So how do you show performance at the application? Okay. So when InfiniBand came in October, they also faced the same issues. So what they introduced is they introduced something called a IP over IP. That means it is a TCP/IP emulation over InfiniBand. That is the IP driver. So it is compliant with sockets. So that's what they were initially able to demonstrate. And these days also, some of the softwares also still use that path. Okay, you may not get the very good latency, but you will get very good bandwidth. Now, what actually the standard introduced is the right hand side, which has all those RDMA, user space, all these concepts we talked. So that's what is called IB native. But what is there? So this is where you cannot program it with the sockets. So this is where what they introduced called bursts. Okay, so that is like the very latest, very lowest level in which you can actually communicate with the network. But then the question is, somebody has to modify these upper level applications or middleware to work with bursts. So that was a challenge 20 years back, but these days all the different modern networks, modern software stack, MPI, even PyTorch, Nickel, everybody has converted into the verse. So you as an end user, you don't have to worry about it. Okay, it is only those people who are designing this middleware, they may need to convert to get the fullest benefit of the InfiniBand stack. So in the next few slides, we'll actually cover this aspect, and gradually you will see we'll bring all these different columns, and then you will see what those protocols means. So just like any other network, I mean, I'm giving an example of InfiniBand, but the same thing when say any other commodity network. So typically you will have an adapter, and in the InfiniBand context also there is let's say network, a collection of switches and routers. InfiniBand introduced some switch and router. The switches are basically used within the subnet, and then the routers which are used across the subnets, and then you need to have some cables. And then when we talked about these multiple layers, what InfiniBand standard did is very basically, we introduced all these, you remember the QP, UKI and all those things. So think of like this, all these layers exist, physical layer, link layer, network layer, transport layer, but they are almost customized or blended together. Okay, instead of a separation, just like what we saw in the traditional TCP/IP does, they're all blended together. So if you take a look at, let's say, network layer, link layer, some of the functionalities, we will not have time to go over all the features. So think of like a buffering, flow control, virtual level, virtual lane, service levels, quality of service, switching, multicast, all these come in that layer. So one of the things, this is what I was saying in the QA session. So all these modern networks, they actually try to use some kind of quality of service. This quality of service, think of like, just like on our regular freeways or roads, ambulance has highest priority, right? Or fire trucks, those are highest priority. Similarly, you can design these networks saying that, okay, this kind of traffic will go with the highest priority. Okay, so they can actually overtake some of the messages. To do that, the InfiniBand specification indicates like for every on the adapter, on every port, you have a set of virtual lanes, and then you can have actually between 2 and 16 virtual lanes. The 0 is the default, and then you have another 15, which is for management traffic. But each one of these have separate buffers and flow controls. And then each switch, including the adapter, can be actually configured. So they have a virtual VL to SL to VL translation. So you can actually configure it based on your traffic pattern, based on your intent and behavior. So in that context, you can think of like you can do actually traffic segregation. And so this is what like a SL to VL mapping. You can also do partition. Um, so the network has different traffic, for example, storage traffic. Okay, or let's say you are running a big um, uh, LLM training. You have to do checkpointing. So you can say, okay, checkpointing is going on some virtual lanes, but might be my all reduced collective is going in another virtual lane, so that they don't interfere with each other. So like this, you can actually configure a network for a desired quality of service objective. So then, of course, routing makes a big issues as the system sizes are becoming very larger and larger. Typically, you need to connect with, there is a topology aspect, then there is a switch aspect. Okay, and then we have a point-to-point communication and also multicast communication. So point-to-point is I can go directly. Each port is associated one or more LIDs called local identifiers, and then multicast, I have to do a kind of a group multicast. So then if you take a look at the switches, the way the switches are being designed, always there is a switch complex. So the basic unit of thing you can think of like a crossbar. So then you take from those crossbars, you build larger and larger switches. Okay. And gradually actually with the demand for large scale systems are coming up. So people are going with the high radix switch, like you see 48 ports, 64 ports, etc. Ben, you raise some hand. Yeah.
Yes, Amir Hossein Sojudi has a question. Is it
Sure.
possible to select the VLs from the user level process?
User level process. Let me see. Yeah. I think Infiniment has some kind of you configure in the VL to SL configuration that you need to do through the like a OpenSN. Okay. But which VL, not the VL, you select a service level. Okay. Not the VL. So for example, like we have done this, like for example, our MPI, which we'll talk a little bit later, MAP software stack, you can say, like, for example, this collected traffic will go through this service level 14 or 13. You can do that. That is a user level operation. But the actual configuration, you have to go through the subnet manager. And in most of the systems, commercial deployment, I don't think the sysadmins gives you access to modify those tables, but they can do it.
Awesome. Thank you.
Okay. So here there's an example. So if let's say these are very smaller, like a 144-foot switch we are saying. So you can think of like these are the leaf blocks, these are the spine blocks. And broadly the Infiniment supports this virtual cut through. And the routing, it can be any kind of routing you can support. The base one is called offstar downstar. You can have shift. Even topology wise also, Fatry is a very popular one, but you can also have 3D torus, the dragonfly, hypercube, any kind of topology depending on your workload and configuration you can do. But here it is trying to show through this example. Let's say I have this P2. P2, I can have one LID or I can have in multiple LIDs. Okay. So if you see, like, let's say why I need multiple LIDs. So I can, let's say I want to send a traffic from P1 to P2. Typically, again, based on the routing in the beginning of the system or even dynamically it gets changed, you have something like a forwarding table. So in every switch, so here example, we are saying, if I want to reach destination LID 2, I need to go through output port 1. Okay. So if the P1 is sending a message, it actually goes and you can see it is taking this path and then it comes and then reaches the P2. I can also send in an alternative manner, like I can also send with a DLID 4. So in that case, what is going to happen? Like this traffic will go through this 4. You see these green arrows. It will go through this spine block and then bring it here. So what it means that with this kind of mechanism, of course, somebody has to support the forwarding tables, but it provides flexibility of adaptive routing. Okay. And that's how these all different vendors use different techniques to provide what they call like an adaptive routing or multi-path selection. There are different terminologies which goes around. So depending on, let's say, for example, if you detect that, yeah, this switch or this path is busy, still I want to reach this P2, P1 traffic can go from here and then come back. Okay. So that's how the basic routing will work. And different routing algorithms will give you different paths. So then multicast, the Infiniment multicast actually follows a very traditional multicast, what we see even in the IP world. Okay. IPv6, typically in the multicast, there is a concept of like a joining the group, removing the group, or so what typically here you can see, like there is a subnet manager here. When you power on the system, the subnet manager goes, they have processes, it goes, discovers the link, it performs those routing table, it configures all those switches, forwarding table, what we saw. And then if we want to introduce multicast, you say basically a multicast join. A request comes, it goes to subnet manager, and then it actually goes and then updates the switch ports. So let's say another another node wants to join the same multicast group. So now you see, so this switch is now configured saying if a traffic comes here, I can automatically do this hardware replication. So that's what. So InfiniBand provides this hardware replication. That was the very initial part of the standard. Okay, InfiniBand standard. And that allowed, like as the system size was becoming larger and larger, you can do very fast broadcast or multicast. The only limitation was that it is based on UD protocols, not associated with RC. So you have to be aware that, okay, packets may get dropped, then you have to have a backup window, retransmission, all those things you need to do depending on the upper layer requirements. But that was the very early days, and later on we'll see in the next section over the years, especially Mellanox and now NVIDIA has been providing more and more intelligence to their switches. And that's what is called in-network computing. And you can do the switches have now more capability to perform operation like all reduce I can do, or data exchange all to all you can do, so that many of these collectives as required by HPC and AI workload can be done much more faster. And similar ideas are also have gone to other networks. Broadcom is working, they call it INC, in network computing, and also like other technologies are also following similar things. So then we talked like this all protocol offload. So this is where let's spend a little bit of time. I think we have another 4 minutes. We'll talk about this different transport types. Okay, so the transport types, it actually comes. There are 2 degrees of freedom. We want scalability and we also want reliability. Okay, so in the traditional InfiniBand standard, if you see these columns, the very strongest one is called reliable connection. Okay, what is the reliability means? That means there are all these things, corrupt data is detected, data delivery is guaranteed, data order is guaranteed, data loss is detected, error recovery takes place. On the other extreme, we have unreliable datagram. There is corrupt data may be detected, but there is no guarantee in the data delivery. There is no data order guarantee, data loss detected, error recovery is not there. So there is a big trade-off here in terms of reliability, but what makes it more complex is the scalability. Okay, you remember the queue pairs we talked? Like before I communicate, I need to establish a queue pair. So if you take a look, let's say, think of like M processes N nodes. Okay, so very simple, like let's say I have a 100 nodes and think of like a M, very simple, is 16. Okay, so every node has 16 processes and I have 100 of this node. Now, if I see the entire system, there are 1600 processes or processors. Okay, and then I actually need, because each one has to communicate with everybody else eventually, depending on your workload. In the worst case, I need this M square N. Okay, like a 25600, am I right? 25,256 00 I need connection. So each connection below, you can think of, like, you remember we talked about all these SCA caching and all those things. So you need some data structures. You need to have some amount of cache. So as the system size started growing, people saw that this RC is not good. Okay, it gives you good performance. It also helps easier to build the upper layers. Because let's say I'm building upper layer, I don't have to worry about packet retransmission. I don't have to worry about packet drops. I just communicate with RC, and then under the hood, everything will take place. So gradually, as more and more larger system got deployed, so this is where like the InfiniBand standard got revised, saying there is an extended reliable connection, XRC. This is the one which is very latest available, called dynamically connected, or DC. In the Mellanox InfiniBand terminology called DCT. And then there was a reliable datagram, but that never actually worked. And this is where AWS actually extended that to call the scalable reliable datagram. Okay, so we'll come to that. So let me finish this section quickly. So then once the InfiniBand was there in the very beginning, from the early days, Ethernet world wanted to see why we can't take the RDMA, because earlier, even though RDMA was a part of the IB, but if you take a look, RDMA is a concept. All right, you can put it on any network, and this was the very first IORF came and says, okay, under the, even if it is a network, Ethernet below, I can actually have a RDMA support on top of it. And then it was the Celsio was the very first company. There was another company called NetEffect. They actually built this hardware support for iWarp. So that's what you will see iWarp. So it still goes through the verbs, but instead of RDMA, like it goes through over the TCP/IP, but it tries to give you the very similar semantics. Instead of InfiniBand adapter, you see iWarp adapter. Okay, but then there was also a software RDMA or software iWarp also existed, but that was mostly for testing and compatibility. But then over the years, the community wanted actually because the InfiniBand ecosystem was like people wanted some time to learn. Ethernet world existed, so people wanted this kind of a convergence. Okay, and this is where this Rocky started. RDMA or conversion and Ethernet. It is not a standard like an IEEE or an open standard. Michalowicz introduced this initially Rocky V1. This is what if you see, it's like IB transport, it comes to IB network and it works with the Ethernet link layer. But then that was not completely Ethernet. So a lot of the management software stack and all didn't work. So then they introduced the Rocky V2. So that is the very latest Rocky V2. So in this case, you can use purely, you can take an InfiniBand adapter which supports both either InfiniBand or Rocky V2, and you can connect it to an Ethernet switch. So even though all your switches are Ethernet, you should be able to actually communicate. And that's what stands for the Rocky here, you see. So it's very similar, like compare these, both are RDMA, user space. Instead of InfiniBand adapter is Rocky adapter. But if you go inside, it is actually the same adapter. You talk to NVIDIA/Mellanox, it's a very hardware is the same with some minor changes. They sell it as a Rocky adapter instead of InfiniBand adapter. So I think let's close here. I think we can have a 20 minutes break. If there are any quick questions I can answer. Otherwise, we come back and then talk about the GPU aware support and keep on moving.
One question from Sharif asking, what exactly are verbs and how are they different from sockets?
Yeah, so there are like we dropped few slides here. This is a half-day version. There is an R sockets protocol. I think that's what you are referring. RDMA enable R sockets. So there, what happens is like there is an intermediate layer here. Okay, so you go through the sockets, but you still exploit like basically you do like a LD preload, and you replace your current behavior of the sockets. Then you try to impose the RDMA on top of that. Okay, that is kind of the R sockets. So the R sockets has been also available for some time, but gradually it has died down. And there, what you get is like you can send your large messages through R sockets. Performance is very similar, but small messages you don't get the latency. Okay.
And then one more question from Bob Lance. Are both InfiniBand and Rocky V2 lossless? How does the control flow work?
Yeah, we are dropping a lot of materials here because I think at the SC we have a full day version. We'll go into that. So it depends on all those, like you remember the reliability I talked in some of the slides. So it depends on all those, like a RC or UD, depending on which of those transport layers you are actually invoking. Okay, so that's what actually separates out this kind of a lossy versus lossless. Any other questions?
That was the last one in the Slack channel.
Okay, so let's take a break. I think is Nick or somebody is there. I think so. I'll stop sharing and we'll reach back. I think what is the time? 3 o'clock PT.
Yes, we'll take a
Nicole.
minute break. Thank you.
Okay. Okay, welcome back. Hope you got charged a little bit. I posted the question, Bob, about the lossless and lossy. Please take a look at the Slack. So broadly, InfiniBand uses very sophisticated credit-based flow control. So that actually allows like a network layer, link layer to work together to make sure that there is no buffer overflow. And especially, you remember we discussed about the transport protocols. If you go through, if the upper level software stack chooses RC, which is a reliable connection, all the under the hood, even if a packet gets dropped, it gets recovered, everything. So that really makes it like a totally lossless network. On the other hand, the Rocky, even though it is built on top of like the InfiniBand adapters and all what we saw, but Rocky allows InfiniBand adapter, which is converted to Rocky, to work with other Ethernet switches. So that's why we cannot guarantee like a lossless behavior. And there are mechanisms like the ECN and all those things for congestion. There is a lot of things in the literature on the web. If you just do a search, lossy, lossless, InfiniBand, Rocky, you'll get all those information. Okay. If there are no questions, please again follow. Now let me hand it over to Ben. We talked about like the basic connectivity, the issues, CPU to CPU. But as you know, these days the GPU is also becoming very important part of the ecosystem. So what is out there? So let Ben introduce some of these things, and I'll also talk a little bit about the UL Link Ultra Ethernet, and then we'll continue. Okay.
Awesome. Thanks, Dr. Panda. So in any case, so just to give a bit of a history, so about around the turn of 2010, 2011, people had realized that GPUs had been around in HPC clusters for a while actually. Recently a paper from a professor at Stony Brook on GPU-enabled clustering had recently won the Test of Time award at SC. So it wasn't until about 5 years later that people realized that you could easily try to place communication into an MPI library. And so this slide and this slide are a bit backwards, but I'll start with this first. So at a high level, many programmers had tried various approaches to looking to combining CUDA-aware memory management, and now these days GPU, just generalized GPU-aware memory management. And this was done usually at the application level in conjunction with a message passing library, such as MVAPITch or OpenMPI, MPITch, etc. What my lab and predecessors had figured out was how to appropriately pipeline data from process A to process B through an MPI library such as MVAPITch. So as this animation shows, through some efficient pipelining, we were able to transfer data from CPU A or from GPU A through the CPU to the network card across a switch to the next network card, CPU, back to resident GPU memory. And at the time, this gained a lot of performance. Someone muted me, sorry. But in any case, this would eventually become very highly performant. And upon trying to look at better technology, we look at how we could improve upon this. So to go back a couple of slides, the reason we look at GPU direct RDMA. So this now leverages more a bit of the network itself, avoiding CPU-based staging and other PCI devices. And the reason why this came about is if every device is using the PCI bus, then you obtain a lot of resource contention. How can we efficiently push data from the GPU to the network card without involving necessarily system memory or PCI bus or the CPU even? And that is where, as were my lab at OSU, Mellanox prior to being bought up by NVIDIA, and NVIDIA during the early half of the 2010s, were able to develop this GPU direct RDMA technology. And these days, and I'll get into this later, these days it is scaled into other technologies featured by AMD and Intel, as well as enhanced by NVIDIA. And now these days it works across a whole variety of interconnects from InfiniBand to Rocky to Slingshot, etc. So to jump to here, even with initial designs way back in that-bitch 2 GDR release 2.3.1, we're able to see like a full order of magnitude improvement in latency and bandwidth, both at medium and larger message, both at small and medium message sizes. And these days, pretty much every MPI library now has some level of GPU awareness. How advanced it goes depends on the implementation effectively. Getting into more GPU-aware interconnects, we look at the question of what if GPU direct RDMA isn't enough? Because at a certain point, if you're doing intranode GPU connection, you still need to utilize the PCI bus, as GPU direct RDMA has been primarily for internode communication. Enter GPU specific interconnects, and the first one that we'll look at is NVLink and NVLink 2. These are high performance interconnects for dense GPU systems, where if you're going to perform communication between two GPUs within the same node, the NVLink technology effectively bypasses any PCI bus traversals and just performs load store operations. This allows for that super low latency, super high bandwidth communication, as we see with the 5th generation NVLink on a Blackwell architecture featuring almost 2 terabytes per second of data bandwidth. This also scales out even further to the NV switch topology, where among say for example DGX machines, which historically have had somewhere up to like 8 GPUs per node and 8 network cards per node. Each of these GPUs is connected to each other via NVLink, and to help manage that more efficiently, we have this baseboard here, where our bisection bandwidth gets up to 2.4 terabytes per second. Just as a reminder, this built on top of the NVLink technology that was presented in the previous slide, and that allows users to take advantage of more efficient GPU to GPU communication. Now, one way of leveraging this is through specialized algorithms and MPI libraries. Another way is, if you want something more streamlined, you take a look at communication libraries. So, in particular, collective communication libraries from specific vendors. The case study for NVIDIA, for example, is Nickel, NVIDIA's collective communication library. And its main motivation, as larger and larger machine learning and deep learning workloads were made capable on high performance computing clusters, is that Nickel was geared towards these larger messages. So not just single digit megabytes, but also looking at hundreds of megabytes, gigabytes of data, at least in today's systems. Presently we're looking at Nickel. Presently we have Nickel version 2, but prior to that, it evolved from looking at only multi-GPU connections and communication to multi-GPU, multi-node. And DGX systems, in today's Grace Hopper systems, Grace Blackwell systems, and the future ones that'll be coming up soon enough. Through Nickel, users are able to, achieve up to half an exaflop, at least as of the publication of this particular blog, showing half an exaflop on 1 trillion plus parameter GPT-like models. And this is in the case of using 3D parallelism already, where you may have data parallelism, layer parallelism, and either spatial or tensor parallelism, all working in tandem to increase more efficient memory usage, speed and training of your model, etc. On a separate facet of this area of hardware design, we look at AMD's Infinity Fabric, which has been published as a cache coherent interconnect data fabric. So I would like to assume everyone understands what cache coherence means in this case. In this case, we're not just looking at cache coherence across CPUs and chiplet designs that AMD largely uses, but also now GPUs as well. Each socket, for example, can get up to, at least at the publication of these articles, can get up to 145 gigabytes per second DRAM per bandwidth per individual socket, and then up to between two graphical compute dies, such as those on the 200 MI 250X. You can get up to 400 gigabits per second bandwidth. So to put that in context, think this is already in place on systems like Frontier and El Capitan, where both are already these massive large scale AMD systems. So this is already heavily used and heavily optimized. Similarly, where instead we have nickel, where NVIDIA we have Rickel for AMD, and these two, and like nickel, Rickel offers similar, if not the same, benefits for communication for larger message sizes, even on AMD based systems, AMD GPU enabled systems, where instead of having NVLink, we have PCIe and XGMI interconnects, and then internode. We don't just deal with InfiniBand, Rocky, and say Slingshot, for example, but also taking advantage of AMD's own Infinity Fabric. Before I hand it back off to Dr. Panda, are there any questions in the chat or in Slack rather?
Yeah, I answered one. Yeah.
So, okay. Do you want me to,
let me share. Yeah.
Yes.
You can see my screen.
Yes.
Okay. So just to give you a little bit of perspective, so I mentioned this earlier. If you remember, like the PCI Express Gen 3, and then we talked about all the CXL and all. So even the NVLink started a few years back with the introduction of the system called Summit. So if you remember the Oak Ridge Summit, that was the #1 system. Now, by the time PCI Express was like a Gen 3, okay? So the earlier GPU deployments, if you remember, like it used to go through a PCI switch. So you connected, then come out, and then you have multiple GPUs. And NVIDIA at that time was ready to have dense GPU deployment. That is kind of a very early stage, early years of scale-up technologies. So they wanted to combine, or a single node having multiple GPUs, like a 4 GPUs and all. But PCI Express Gen 3 was not able to handle that. So that actually was a collaboration between Mellanox that time and NVIDIA and IBM. And IBM has their PowerPC infrastructure and the CAPI support. So they were able to work together to bring this NVLink, which was very easily being connected to the PowerPC. That's how the NVLink started, and the IBM, the Summit system was designed. But then over the years, what is happening is, of course, the NVLink is there. We just saw like the Infinity Fabric is also from the AMD. They are going along the same direction. But now there is a big competition is happening because people want to have more and more number of GPUs within the same node or even the same rack with very low overhead in the latency. And this is where the Ultra Accelerator Link, or the UL Link consortium has been initiated. And again, it allows, like if you see, for easy plug and play alongside interconnects such as CXL, PCIe, XGMI, AMD Infinity Fabric. So it is directly trying to compete with NVIDIA. And then the version 1 is standard is available. But while this scale-up war is going on, the similar war is also taking place on the scale-out. And that's what has led to Ultra Ethernet. So we'll talk about, of course, the InfiniBand has been there, and the Rocky, it has been there, but the Cray Slingshot, which led actually to the #1 system in the Cray Frontier system. So that actually, they exposed the upper layer through Ethernet. Okay, so that has led to, especially in the last few years, saying that even though Ethernet was always associated with higher latency, now Ethernet can actually deliver high performance, including lower latency. So that is the newer kind of consortium. All the different kind of Ethernet vendors have come together and have defined this called Ultra Ethernet or UEC, the stack. The goal here is, as you can see, like the tail latency should be minimized. It has all this multipathing, packet spraying, flexibility in the delivery order, end-to-end telemetry, and directly it is trying to address some of the shortcomings which are there in the Rocky and IB. And as they are also trying to handle the scale out, a portion of that is also coming to scale up. So this is where there is a new kind of a standard called scale up Ethernet or called SUI is being introduced. So this is exactly again alternative to NVLink as well as UA-Link, and is broadly being driven by Broadcom. So and together with this, they are also I mean, it's a part of, you can think of like it's the same Ultra Ethernet consortium. Ultra Ethernet started with saying it is scale out, but SUI is now trying to say, okay, we can also implement that scale up, so that the entire network, both scale up and scale out, will be Ethernet. And at the same time, also Broadcom is trying to introduce. I indicated this in network collective computing, or called INC Inc. This is very analogous to NVIDIA SARP. Okay. So just like the SARP, we'll go into a little bit more details in the next section, in the SmartNIC section, but the idea is very similar, so that the network can have intelligence and it can actually do collective operations like all reduce, all to all, etc., much more faster. So it is a very exciting phase. And on the Slack, I think Bob indicated also there are a lot of initiatives are happening with optical, with photonics. So the broad idea is that how we can bring a lot of devices sitting closer to each other. That is the kind of the scale up. So that is, it will be dense architecture, and with a very low latency and high bandwidth, people can actually have access to, let's say, thousands of GPUs. Okay, so the next few years will be very exciting along these directions. Now, before we go into the smart network interface, let me talk about at least there's two of these other interconnects. One is the Amazon EFA, and then the Cray Slingshot, which I just mentioned. So Amazon AWS, this is taken from one of the earlier like AWS online tech talks. In the very old days, AWS, of course, they came from the data center. And in the earlier days of the cloud computing, as if you some of you remember, the cloud computing was not very fast actually earlier. And especially with the AWS, if you see, they have gone through multiple generation, starting from 1 gig to 10 gig, then had a C3 version, C4, C5, and then the very latest one is C5N. And if you take a look at here, this is an adapter they developed in-house, and have been deploying in their AWS cloud environment, and they expose through through a leaf fabrics interface. We have some detailed discussion later on. And what I introduced here, they instead of RC, they support UD, but they have this new transport protocol called Scalable Reliable Datagram, or SRD. Okay. Now, over the years, like they have this multiple generation of adapters, and intentionally, if you see, their latency is higher compared to others. Okay. Whereas other vendors and all are trying to optimize latency, but by design, because they have like a distributed data centers and they want to have the same uniform underlying infrastructure, both in their cloud as well as in their data center, and they follow of many of these like a multipath routing and all. So they have been like, when they started in 2018, it was very high, 14 microseconds. So if you have an application which requires very extreme low latency, you may not get very good performance on the AWS. Whereas if it is a latency tolerant application or the modern day AI workload where the large messages matter, you will not see much difference. So that SRD, if you take a look, this is where it sits. Okay. So they are able to actually, their objective is to, if you think of like that M process and N nodes, it's only with M QPs per SCA, they are able to actually get this scalable reliability so that they are able to detect corrupt data. Data delivery is guaranteed. They don't guarantee data order. That needs to be maintained by the software layer. And then data loss is detected and they can recover error. Okay. So this is the feature they provided. In fact, we worked with them in the very early days. When we have publications, we try to show how MPI layers can be actually designed. And if I go back here, nowadays you see these lip fabrics based works. I mean, so there is all different MPI, Intel MPI, Open MPI, MPH, even NVIDIA Nickel has a support. So all these upper layers are able to take advantage of that SRT. So next, if we move forward, another scale out network, we'll take a look at the Cray Slingshot. And these came actually, so this is a kind of a proprietary network, but we are adding here just to give you a perspective, like how the commodity is moving, but at the same time, proprietary network is also moving. So this has been taken from um, some of my colleagues and I used to do a Exacom workshop at ISC. Some of you might be familiar. So there was a keynote talk by Steve Scott. He was the CTO at that time, HP Cray. So some of the slides are from there. So this is their 8th generation scalable interconnects. So the idea is that they can have like up to 250K nodes. It is Ethernet compatible. That was one of their objectives, and supporting adaptive routing, quality of service, congestion control. And this one we'll talk a little bit more in the next one called tail latency. Okay. So a lot of these networks, if you do some more in-depth measurement, of course, there is a lot of data, but then people compare and contrast. Some are vendor data, some are non-vendor data. The objective is that, okay, on average, if I send a message from one node to the other node in the entire system when the application is running, of course, a lot of these traffics get delivered on time, but some percentage of the traffic actually takes a lot of time. And if you think of like any parallel application running on the system, if those some of the packets or some of the packets take more time, then it significantly degrades the performance and scalability. So this is where the objective is that how we can reduce that tail latency. So here they provide these two kinds of features. Like we'll see from the QoS perspective, I talked about this a little bit earlier. We discussed these service levels, virtual lanes. So very similar to InfiniBand and other networks, they provide a QoS classes. You can actually support multiple overlaid virtual networks. So you can actually define the traffic classes. As just like here it says, head of the line blocking, you can avoid. Like for example, you don't want like a very small message getting stuck behind a very large message. Like one node is trying to do a 1 GB IO transfer, and another process from the same node is trying to do a 4 byte reduction. You don't want that get too stuck waiting for a long time, just like what we see in our normal sometimes on the roadways. The other one is this congestion management. So they have very in-depth hardware automatically tracks all outstanding packets, knows what is flowing between every pair of endpoints, quickly identifies and controls causes of congestion, so that they send that information to the source. Okay. And of course, other networks also have started doing a very similar thing. So whenever there are like a congestion, you need to very quickly identify why or where that congestion is coming from. If you can detect that on a very large network and throttle the sender, then it will free up the buffer space for everyone else. Other traffics are not affected. It avoids HOL blocking. And that's what exactly they have implemented in the Slingshot. And that's why it was chosen. Like when the Frontier came, prior to that, the Department of Energy, they keep on rotating different vendors, different like Summit was like a NVIDIA GPU and InfiniBand, but when they moved to the Frontier, it was AMD GPUs with Slingshot. Okay, and similarly Livermore also, they had earlier some of the InfiniBand systems like Lassen and all, but then it moved to the LCAP, which is also AMD GPU Slingshot. Aurora is Intel GPU Slingshot. So like this, all the different large scale systems they deploy, especially DOE plays with the different vendors to make sure that their technologies remains very competitive. So these are the kind of the very high level objective of both scale up and scale out network. Again, since it is a half day version here, we are not able to cover everything. I know many of you have a lot of questions. As I said here, this tutorial also has been accepted for the upcoming supercomputing conference. We have a full day version. So we'll go into much more details, very similar to also the high performance deep learning tutorial I gave it in the morning here. That also will be presented as a full day version. Okay. And also we are presenting this tutorial as a full day version in in another 10 days at IEEE cluster in Edinburgh, Scotland. So if any of the European people would like to attend that, we'll be very happy to again present there. So with this, let me then hand it over to Ben. I think we'll take this section and some of the remaining sections, and I'll come back towards the end. Are there any questions?
Hang on, here we are. Sorry, I forgot I was muted. So again, Dr. Panta,
Yeah.
to answer your thing, there are a couple of questions in chat
Okay.
for you
Okay.
that I'll let you take care of.
Okay.
Now, yeah.
Go. You continue. I'll try to answer those. Yeah.
Sounds good. So yeah, so as I said, and I realized I was muted. Now we're looking at the overview of smart networking technologies. As Dr. Panda mentioned earlier, this is kind of what this is where you start seeing that executive secretary model where the secretary starts having, say, the equivalent of a master's or PhD level education. In this case, how intelligent is your network, or how intelligent are your network components in terms of can they offload certain things? So just to kind of give a precursor, many folks are familiar, I presume many folks in the audience are familiar with collective operations. And so in this case, like simple one to one, more of them could be all to all communication that I'll look into. Many of these communication types or communication operations are supported by, say, NVIDIA's SHARP, Scalable Hierarchical Aggregation Reduction Protocol. And while reduction is in the name, the APIs are available also for broadcast for items like broadcast and all reduce, which already has an aggregation. But basically, this is one of the first earlier instances of, say, a smart networking approach. So here we look at Sharp in a basic example using tree topology, using NVIDIA's or InfiniBand's like fat tree topology. So in this case, for starters, every entity at the base of the tree, every node, starts off initializing your in-network offload. And then as soon as that is done, or as soon as a collective operation is called, we take a look at sending these data to the switch. And then every subsequent switch keeps aggregating this data and sending it up to a higher level in the topology in the tree. In particular, trees are really good for this just because it forms a natural recursive aggregation before we broadcast everything back down to the processing elements. And it's this that allows for even in the case of, say, blocking collectives, you can get this level of asynchronicity, where you get to overlap this communication and computation together. But the downside of this is that in some cases, if you were to, say, customize this with, say, P4, for example, and do non-sharp based operations, you may not always get, say, floating point operations done. And the technology is limited. The technology in the switch is limited to a degree just because it has to perform an enormous amount of routing on top of this. So what has come in more recent developments has been smart network cards. So now we're pushing the intelligence from the switch to the adapter, to almost the adapters themselves. And this was a question earlier on. very early on in the made by Indira. And so this gets really into what makes a smart network card or smart NIC intelligent. There are two broad types of these smart NICs. One of them is a more system on chip based, where you have a network card plus programmable CPU cores plus ASIC chips. And then the other option is FPGA based NICs, which have been around a bit longer in terms of the smart network card area. Broadly speaking, broadly speaking, smart NICs and data center processing units in general have been featured initially in the cloud environment. What this means, just because when you start getting into cloud environments, excuse me, in data centers, managing the hypervisor is a lot of work for a server CPU, even though these things are beefy. If you can push that management to the network, it alleviates the strain on the servers themselves to perform compute or whatever or any other operations. Given the popularity and the I guess availability of Bluefield DPUs, most of the development, to my knowledge, and to the HPC world has been developed on these network cards. What this means is we deal with system on chip cards connected to your host server, where you have your ConnectX RDMA adapter, a switch, a PCI switch, ARM cores, and DRAM local onto the DPU. I'll answer see Dave's question. To my knowledge, I've only gotten to play around with a system on chip with only ASIC and system on chip based ones. The usage, there are FPGA NICs available in the field. So like there have been in certain HPC papers, folks have used AMD's Alveo FPGA chips, which I'll explain in a bit. The advantage of FPGA based ones is that because FPGAs are meant to perform really well on one specific task, you can flash a design onto an FPGA through say VHDL and mix of high-level synthesis, and that task can be done really, really efficiently. So you lose some programmability, but you gain a lot in performance. But as I've said, I've not got a chance to play with FPGA-based NICs yet. Hopefully at some point before I graduate, I get the chance to. And then Bob's question: if we push in-network reduction to the edge in a smart NIC, if we push the in-network reduction to the edge in a smart NIC, you would still get the advantage of reduced network traffic, just because the system on chip portion would allow you to perform computation locally for intranode communication. Once you get to internode, you would have to rely on the switch a bit more if you wanted to avoid network contention at the card. Does that make sense? Or at least hopefully that makes sense. In any case, just to keep things rolling, most of our research and design has gone into an offshoot of MVAPICH called MVAPICH2 DPU, featured through the company Xscale Solutions. This library features a novel framework to offload non-blocking collectives to DPUs, and I'm happy to discuss it at a high level offline. In particular, non-blocking collective operation has been kind of the way to go, especially at the turn of the 2020s. And further on, you can look at non-blocking and blocking point-to-point and non-blocking broadcast. Each of these the more complex your communication is, or the communication pattern is, the more benefit you may get at offloading. Just because, for example, offloading a non-blocking broadcast gives some benefits, but because of the one-to-all aspect, you can expect a slightly lesser benefit unless you start really scaling your message sizes. Getting into application level benefits, just because we already see near perfect overlap at micro benchmark level, and this comes in, like Dr. Panda said, this comes in with the full day version of our tutorial. We also see substantial benefits in all-to-all heavy applications, such as those using the P3D FFT framework or high performance LINPACK, where we get up to either 17% improvement at super large grid sizes, or up to 17% improvement in GFLOPs and GFLOPs utilized or executed, depending on your problem size. Naturally, in both cases, the more you can only get so many benefits the more like based on a certain scale and problem size. So the more DPUs we have, the more we'd be able to scale this out and increase our problem size to show benefits. So that way we don't entirely saturate our bandwidth at say 31 nodes or 16 nodes. And then to look at Bob's reply on Slack, yes for yeah, the answer is yes for intranode, no for internode, basically. Now, so all this two-sided operation has been done, but has been done before my time. Getting into one-sided operation, as Dr. Panda mentioned earlier, you can theoretically get this mention of 100% overlap with one-sided operations. But if you have particularly dense communication, even with one-sided operations, you may not be able to get that overlap. And so even offloading one-sided operations, which are inherently this non-blocking communication structure, you can still get substantial benefits. So in my designs for non-blocking put and non-blocking get, and here we focus on non-blocking get operations, we utilize a mix of low-level IB primitives and NVIDIA's GVMI guest virtual machine ID, which I can explain more in a full day presentation. We look at both MPI put and get, as these are non-blocking by default, and then in the OpenSHMEM parallel programming model, which has been referred to during the morning sessions. What is it? The morning sessions GPU communication. They have specific non-blocking APIs for put and get as well. And so the emphasis here is on overlap as opposed to say necessarily increasing or improving the raw latency of a get operation. And I want to emphasize that just because offloading is an intensive task, regardless if you do it for two-sided or one-sided. So if you're offloading a small message size, you may not get as much benefit relative to offloading like say 4 bytes versus 4 megabytes. So here, so in these three charts, we look at the block sparse matrix multiplication kernel where we utilize non-blocking get operations or blocking operations depending on the kernel. And so we showcase the benefits of offloading the non-blocking kernel or the communication and the non-blocking kernel to the DPU, where we see up to this 90% benefit in increasing large message sizes, where this 40 by 40 mesh results in message sizes of up to 1.5 megabytes or so being thrown around. The 60 by 60 mesh size in when we have more dense communication for 4 nodes, full subscription on an AMD EPYC cluster plus BlueField 3s, we still get up to like 45% benefits when we're going up to 2 megabyte message sizes. As a bit of an aside, and I'll get into this a bit more on the next slide. We look at BlueField SmartNICs and other SmartNICs can be used for compute offload. The common naive variant is just to offload more core, just to treat the DPU system on chip cores as an extra set of cores for offloading portions of compute where we get up to this 99% benefit in certain cases. But this is just naive. This just follows the naive policy of add more cores, which you could also do in your pure server CPU. But what if you don't want to do that what if you don't want to do that or can't do that and you need to do some more smart compute offload to the network? My former lab mate Kaushik, he has since graduated, analyzed smart compute offload on BlueField 3 SmartNICs. So in this case, he looked at linear algebra operations, which are ubiquitous in high performance computing, stretching all the way back to LinPack, for example, and looking at a mixture of vector multiply add, distributed dot, and matrix vector products. He is able to design a scheme for more intelligent compute offload to the DPUs. So we're not just talking in-network compute, as Bob had asked in his question, and as I mentioned with Sharp earlier, we're looking at can we offload more complex operations as well, such as matrix operations or full-on functions. And here we can still see the same benefits where if we're given the right problem size, right scale, right amount to offload, as how much to offload is also an important question. We can see up to 24% improvement on, or 10%, 15%, 24% improvement on systems, depending on the generation of your CPU and the network involved. Before I continue on to the other smart NICs involved, does anyone have any questions? I already see Bob typing. But yeah, I realized I blew through this very quickly. As Dr. Panda mentioned in our upcoming full day tutorials for at IEEE cluster and SC, I will go into this a lot more in depth. Okay, I can answer the questions later then.
Yeah, let's continue. Yeah.
Yeah. So going on to other competitors and vendors in the field, AMD for the longest time has had Alveo smart NICs through also either themselves or through talking with Xilinx, for example. And in their Alveo smart NICs, which I mentioned before, are common items. These feature both a small amount of compute for the ARM processor, but the biggest part is through the use of their UltraScale plus FPGA. And the FPGA portion in particular has programmable data plane pipelines for quality of service, IPsec for security, tag matching, and these things have been featured a lot more in NVIDIA's BlueField 3 smart NICs as well for hardware tag matching, data path accelerator, as has been mentioned before, so on and so forth. The Pensando data center chip has a P4 programmable custom match engine, and this is good because while we start getting into smart NIC specific programming, you ideally could simplify it enough to have a basic hardware tag matching engine and be able to still do offload through the ARM cores here. And as with BlueFields, you still have your data encryption and storage offload for security and traditional cloud data center aspects. Intel for the longest time has been working on their own FPGA-based smart NICs. You have your infrastructure processing units, as they're called, and then FPGA-based smart NICs. Each one performs some level of offload for storage and security and network protocols. And each one has their own pluses and minuses, such as the FPGAs being able to accelerate infrastructure applications, but not be able to offload. And the IPUs are a bit more of an advanced version. And over here, and then this slide just covers a diagram of both of them. So given an Agilex FPGA, you have certain spots. You have your DDR4 DRAM, precision clocking for input output, Ethernet control, etc. In their IPU, they have a more dedicated packet processing engine and an ARM-based compute complex. So this comes back to a slight system on chip, but not entirely system on chip. Getting into the next portion, as Dr. Panda mentioned before, we can look at network-based computing for HPC all day, but in more recent years we've looked at network deployments for AI workloads, and so we are going beyond general purpose computing into more specific domain-specific hardware designs. So in the first one, we look at Cerebras, and in particular, they have their third generation wafer scale architecture. So just to give a sort of size comparison between at the time an H100 and the WSC3 wafer scale architecture, we see a 4.5 times increase in transistor count. Hang on. I'm off by an order of magnitude. My bad. Add another 0 to that, and we see a substantial increase in the silicon and the amount of silicon used for these things. So, for example, an H100 will fit in both. You can carry that with your hands easily. A wafer scale processor like Cerebras may take up an entire table, for example, or for example, maybe like a couple of more than a few 24-inch monitors stacked together. These things have an exceedingly powerful bandwidth or memory on chip SRAM, the same RAM used in your caches, for a whopping 21 petabytes per second. And these can be hooked up to external memory of up to 1.2 petabytes. An interesting innovation that's been brought back and forth over the years is an on-chip interconnect. In this case, this is formed in a 2D mesh, that Cerebras calls Swarm for simplicity. And this allows for very, very efficient point-to-point collective communication through networks on the wafer scale chip itself. as opposed to going through, say, SRAM, or if it had a DRAM, DRAM. And this goes up to 214 petabits per second. This next slide shows how thanks to a mix of all of these, you're able to perform linear scaling on an increasing number of even wafer scale Cerebras like CS2 nodes. Devin Bidstrup asks, how bad is the yield on a wafer scale processor like the Cerebras wafer scale 3? Personally, am personally I don't think it'd be a bad I don't think it'd be a bad yield. I've never had a chance to play with it. Dr. Panda, do you have any further insight on this?
Yeah,
First,
I mean, some of the other team members like Quentin and all, we ran some of those things on their earlier system, but not on the very latest version. Yeah.
okay, that'll be a Quentin question then. Um, but yeah, so Devin, I can forward your question to an internal team member, and we can get back to you in a short enough time. I'm sorry for the trouble. So moving on to another domain-specific architecture or domain-specific AI processor, we look at Habana Gaudi, which more recently has been purchased by Intel. And by recently, I mean the past like 4 or 5 years. This one is a more fully fledged. This one kind of follows the tradition, a more traditional CPU processor approach. However, in this case, it looks at more. It looks at tensor processing cores and SIMD operations and matrix operations. And compared to, and at least to my knowledge, unlike Cerebras, it has more explicit support for increasingly low precisions, as has been the norm for AI for increasingly large AI workloads. This one features 32 gig capacity HB RAM or high bandwidth memory RAM in 4 different modules, up to 1 TB per second bandwidth. So this actually has some relegation. Actually has some commonality with the A64FX, which features a similar CPU bandwidth. But in that case, that's a general processor. This one's purely for AI. This one, unlike other potential contenders, this one focuses more purely on Rocky V2 connectivity and has Rocky engines on the chip as well, both for scale up as well as scale out between different Habana Gaudi chips in a potential HLS Gaudi server. Habana Gaudi has their own collective library, HCCL or HICL, for communication support. And just to give an example, the more we can showcase what this will look at the throughput in terms of tokens per second looks like, the more Habana Gaudi processors we have, going from 256 to 512 to over 1,000, and we're able to get over 100. We're able to get over 100 tokens per second. So that covers more domain-specific architectures for AI workloads as well as smart networking technologies. Before I continue, does anyone have any questions? At the very least, I can answer. I'm happy to take these offline after the fact as well. If not, I will happily go into the next portion of software
Yeah.
stacks for commodity high-performance networks. So now at this point, we're gonna start taking a look at everything that's been discussed here and start going up the stack again for high level, going from going from just network communication to transport libraries to MPI libraries. And so to start, we'll take a look at Open Fabrics. The organization is still intact, and it started out as an OpenIB association. They have an annual workshop every year. This was meant initially to incorporate IB, Rocky, and iWarp in a unified manner. So in this case, because at the initial opening of it, Windows was still very heavy usage in Linux in servers before Linux kind of took over. Support is there. The latest stable release is OFED 4.17-1, and initially the naming convention was independent of the Linux kernel, but these days it's trying to get aligned, and OFED 5.3 is under development at least as of recent. The benefit of this is that users can download the entire distribution and then just run it completely out of the box with some minor tuning as needed. And this kind of branched out into 2 separate camps as the years have gone on. We have one camp for IB and Rocky, and we have another camp for practically every other interconnect, EFA, Slingshot, etc. And I'll cover the first camp through Unified Communications X, UCX. It's been UCX primarily has been an open collaboration between industry, lab, and academia for minimizing that bottom line for low latency, high performance interconnects. And it's used heavily to this day in both traditional HPC workloads and AI workloads, both standalone as part of MPI libraries. UCX is also part of a much larger consortium, including the UCC library, the OpenSnappy project, HPCA benchmarks, and so on. The other camp has been the libfabric software stack. So this is a much more per provider vendor specific implementation where different vendors such as Cornelis Networks or the folks working on Verbs or Slingshot or EFA, etc., can contribute transport layer performance to a larger body of code. And when end users download that code base from their GitHub repository, they can configure the library to run specifically for either IB verbs or EFA or Slingshot or Omnipath Express, PSM2, PSM3, etc., or a combination thereof, depending on the compatibility of the system. And so again, in this case, this is very vendor dependent. Each one individually contributes to their own provider, as opposed to a single streamlined thing such as UCX. Each one has their pluses and minuses, effectively. Sticking with InfiniBand, as that has been Dr. Panda's labs expertise over the past 25 years. InfiniBand, while may not as performant in some cases as a Slingshot, or at least in terms of taking the top level performance, it is still very relevant. 54% of clusters still 54% of clusters still utilize InfiniBand fully. And even though it is no longer the majority of it no longer takes up more than 50% of the performance, it still makes a majority or a plurality of clusters compared to gigabit Ethernet, which in this case for the top 500 purposes also includes networks like Slingshot or Broadcom aware networks. So just to clarify here, this portion of the pie chart is an amalgamation of multiple network types or network vendors and types. And I'll get into that in the next couple of slides. So here, just to make an example, we showcase the amount of the larger InfiniBand installations in the top 500, including a Jupyter booster in Germany or Nebius in the Netherlands or plenty of Microsoft Azure clusters. One thing to note here, as well as the larger top 500 list, is that especially coming from Microsoft Azure, is that many cloud deployments have become advanced enough and powerful enough to make these top 50, top 100 positions in the top 500. A few years back, there was a 4-in-a-row section of Amazon AWS instances, all of identical core size and interconnect speed, and they made the top 500, and not just like the bottom 100, but like even the top 200, 100. And they are mostly in this Ethernet-based installation. So for example, here, the majority of these installations are Slingshot based. However, we see installations such as BXI, Broadcom Net Extreme, NVIDIA Spectrum X. Seeing a question from Devin about portals. Portal. You want to go take care?
I can answer. Yeah. So if you go into this Ultra Ethernet consortium, it is actually portals. A lot of ideas from portals have been taken there into the Ultra Ethernet. And some of these portal concepts also has gone into the Slingshot. And Slingshot, as we are seeing in this on this slide, is actually trying to provide that Ethernet-based solution. So in fact, earlier this week, I think I mentioned in the morning tutorial, we had this 13th annual MBAPIC user group conference. In fact, we had a talk from Keith Underwood from HPE on the last 30 years of Ethernet. So if you take a look, you will see the connection between portals and the Ultra Ethernet Consortium. I believe his slides are linked. If I'm not wrong, just go there. I'll just post the link. It's mock.map each. Uh,
Okay. Thank you so much, Dr. Panda.
yeah.
I'll continue from here. But yeah. So with both this slide and this slide in mind, we take a look at some commodity interconnect trends in the last 10 years. When Rocky was first introduced at back in 2015, there was a huge outpouring of popularity for it just because many folks even today, system admins, network developers, network engineers, they're familiar with Ethernet, and just adding RDMA over conversion enhanced Ethernet made it a very popular choice. However, prior to the Ultra Ethernet Consortium being like as fully fleshed as this today, when AI demand required more HPC mature interconnects, and I put that in quotes because just because while Ethernet has been around as an interconnect, InfiniBand having been the dominator, a solid dominator of the HPC market for a long time, kind of came back into popularity, not just partially through NVIDIA's adoption and use of it, and also partially through the fact that every DGX SuperPod and HGX machine from 2023 onwards and beyond have come equipped with InfiniBand plus NVLink plus NVSwitch. And this, just to clarify, this is just at least through the start of January of this year. How things will change with more Ethernet installations, as of right now, we cannot predict. But what may happen next? This is just as real time as we can get with this setup. So so into the next spot, we'll take a look at case studies, both at the low level performance. So this is case studies between InfiniBand and say R sockets or pure sockets performance, and then later on we'll get into message passing interface performance. So to start off, we look at Rocky versus IB EDR comparison. So at the time that these were taken, we were at ConnectX version 4 and using 100 gigabit per second connection across Rocky and InfiniBand. In either case, both perform very closely together. Both perform very well to a point, but because of some of the extra processing at the time that InfiniBand was able to minimize over Rocky, it's able to consistently get this performance improvement going from say 0.86 microseconds to 0.73 for small message latency, or say sub 12,000, say 11,800 megabytes per second versus hitting line rate with InfiniBand EDR. Same thing can be said if we're relegating ourselves to elastic fabric adapter when using either the unreliable datagram or scalable reliable datagram. And this was done again a couple of years back when on the C5N large instances. For example, in this case, while SRD starts dropping up performance at 128 bytes, for example, in terms of small message latency, or it'll do it more so quickly. We're able to see, or no, it drops off message rate. Sorry, my bad. The UT ends up holding out a bit longer before it actually starts dropping off into the low 1.5 million messages per second bidirectional, and then similar thing for unidirectional and ping pong latency. These were some earlier and more recently verbs level evaluation of Broadcom Rocky adapters. At the time of these getting taken, Rocky was not as developed as it is today. So at small switches, we see this 3.37 microsecond, whereas on IB we may see 1.5, 1.6. The numbers have gotten better since then, and we will provide updated numbers in our full day presentations and future ones. And then similarly for bandwidth, even with this in mind, we still hit line rate over here. Now that we get into the message passing interface performance, as many of you may know, my lab develops the MVAPICH MPI library, As an open source MPI library that's been around for 24 years and counting. Dr. Panda loves telling this anecdote everywhere. When we first demonstrated our open source version at ST 2002, it was an 8 node cluster, not 80 or 800 or 8,000, but just 8. And at the time, that was as stable as things could get before. That was as stable as things could get in terms of InfiniBand, and it's amazing to see how far interconnects have come since then. As of recent, we have an open source flavor, and in order to kind of reduce the amount of extra flavors that we have in these subsequent bullets, we've introduced MVAPitch Plus as a unification of MVAPitch 2x, which is like our secret sauce implementation, and MVAPitch 2 GDR, our GPU-aware implementation for AMD and Intel and NVIDIA GPUs. As of right now, we support the latest MPI 4.1 standard, and as soon as MPI 5 implementations come out, you can be sure that will be there. We also developed the OSU micro benchmark library, which has been one of the many de facto ways to benchmark MPI implementations on HPC clusters. So marketing spiel over. Let's get into some actual numbers. So one thing to note is that over the years we've carefully benchmarked so many network level implementation or network level properties, in particular small message, large message latency, going from QDR all the way to NDR. One thing we'd like to know is that in terms of this performance over here, the stickler for NDR, is that despite being the latest InfiniBand switch in network, ARM processors and having a dense ARM processor core, for example, such as NVIDIA's Grace, results in this slight degradation compared to Intel processors, given a smaller core count, smaller distance to the NIC, at least for small message sizes. Getting to larger message sizes, we were able to saturate the bandwidth fully and still maintain that continuous lowering of larger message latency. This also gets reflected when we do unidirectional and bidirectional bandwidth, where as we hit that 1 MB message size and beyond, you can see we're still not quite there in terms of saturating the bandwidth. Give it another 2 or 4 MB, give it 2 to 4 MB messages, and we would cap out over here for both cases. Moving into unidirectional and bidirectional bandwidth, again, same thing we see the same thing at the MPI level that we saw at the pure network level. At the time that these numbers were taken, Rocky had a slight performance degradation compared to IB. These days they're much closer in nature and performance. And we still see competitive results on Slingshot 11, hitting line rate for unidirectional and bidirectional bandwidth. And same thing can be said for Broadcom. Before I get into the hands-on exercises, does anyone have any further questions in the Slack?